Imagine a universe so vast that it contains more stars than there are grains of sand on every beach on Earth combined. This staggering reality invites us into an exhilarating journey through space, where the wonders of our solar system collide with the enigmatic forces that govern the cosmos. From the majestic rings of Saturn to the fiery storms of Jupiter, every celestial body holds secrets waiting to be uncovered. We will delve into the mind-bending mysteries of black holes, unravel the threads of dark matter, and explore theories that challenge our perception of time and reality. What do these cosmic puzzles reveal about the very fabric of existence? The formation of the solar system is a captivating topic filled with intriguing mysteries that continue to puzzle scientists. It all began around 4.6 billion years ago with a massive cloud of gas and dust known as the solar nebula. As this cloud collapsed under its own gravity, it spun rapidly, forming a flat disk. Within this disk, solid particles began to stick together, gradually forming larger bodies known as planetesimals. This process eventually led to the creation of planets and other celestial bodies. One of the most fascinating mysteries surrounds the process of planetary formation itself. For instance, why did the inner solar system develop rocky planets such as Earth and Mars, while the outer solar system became home to gas giants like Jupiter and Saturn? Scientists hypothesize that temperature differences within the solar nebula played a crucial role. Closer to the Sun, where it was hotter, only metal and rock could condense, leading to the formation of terrestrial planets. Meanwhile, in the colder outer regions, lighter materials like hydrogen and helium could remain, allowing gas giants to form. Another compelling question relates to the presence of water on Earth and other celestial bodies. How did this essential ingredient for life make its way into the inner solar system? Some researchers suggest that comets and asteroids, which are remnants from the early solar system, delivered water to Earth through impacts. Others point to chemical reactions in the solar nebula as a potential source. This ongoing debate underscores the complexities of our solar system's origins and the pathways life took to find a home on Earth. Furthermore, there is the mystery of the irregular orbital characteristics of some comets and asteroids. Many of these objects possess strange orbits that seem to defy the orderly arrangement we see with the planets. This could be influenced by gravitational interactions with larger bodies, or even the presence of undiscovered clusters of matter beyond the known planets. Each of these questions presents an opportunity for deeper exploration, fueling our understanding of not just our solar system's past, but also its future. The quest to discover and study exoplanets, or planets outside our solar system, has blossomed significantly over the past few decades. Astronomers employ a variety of sophisticated techniques to identify these distant worlds, with two primary methods leading the charge: the transit method and radial velocity method. Each offers unique insights into the presence and characteristics of exoplanets orbiting stars in our galaxy. The transit method involves monitoring the brightness of stars. When a planet passes in front of a star from our viewpoint, it blocks a fraction of the star's light. This dip in brightness can tell us not only that a planet exists, but also its size and orbital period. Space telescopes, such as Kepler and TESS, have revolutionized this technique, detecting thousands of exoplanets by observing the dimming of light from countless stars over extended periods. On the other hand, the radial velocity method requires a different approach. It relies on observing the wobble in a star's position caused by the gravitational tug of an orbiting planet. As a planet exerts its gravitational pull, it causes the star to move slightly, resulting in detectable shifts in the star's light spectrum due to the Doppler effect. This method has been instrumental in confirming the existence of many exoplanets, especially those that might be too small to cause significant light dips. Once identified, scientists analyze the atmosphere and composition of exoplanets by studying the light that passes through their atmospheres during transits. This analysis can reveal the presence of various gases, providing clues about potentially habitable conditions. The continued advancements in telescope technology and methods mean the field of exoplanet research is rapidly evolving, opening new windows into understanding these distant worlds and their potential for life. Titan, Saturn's largest moon, stands out in our solar system as a fascinating candidate for hosting life. One of the most compelling reasons for this consideration is its thick atmosphere, which is primarily nitrogen, much like Earth's. This dense atmosphere subjects its surface to a rich array of organic chemistry, providing compounds that are crucial for life as we know it. This chemistry offers tantalizing clues that suggest Titan might have some fundamental building blocks essential for biological processes. Beneath its thick clouds, Titan harbors lakes and rivers filled with liquid methane and ethane. While these hydrocarbons are quite different from the water that sustains life on Earth, their presence hints at complex chemical processes that could occur in Titan's intriguing environment. The surface temperature on Titan hovers around -290 degrees Fahrenheit, making water ice stable, and these frigid conditions allow for unique forms of chemistry. The Titan atmosphere could even support microbial life that thrives in such extreme environments, demonstrating that life may not be limited to familiar conditions. Moreover, scientists speculate about the possibility of a subsurface ocean beneath Titan's icy crust. This ocean, potentially composed of salty water, could provide a suitable environment for life. Just as Earth's oceans teem with diverse ecosystems, a similar hidden universe beneath Titan's surface could host life forms adapted to extreme conditions. The search for life on Titan has grown increasingly sophisticated thanks to missions like the Cassini spacecraft and the upcoming Dragonfly mission, which aims to explore Titan's surface and its organic materials directly. Ultimately, what draws researchers to Titan is the combination of its dense atmosphere, intriguing organic chemistry, and potential for subsurface water. These elements coalesce into a rich environment that could harbor life, challenging our understanding of where life can exist. As we continue to study Titan, we edge deeper into the profound question of life beyond Earth, with Saturn's most mysterious moon leading the charge. Enceladus, one of Saturn's icy moons, has astonished scientists with its geysers that erupt water vapor and ice particles into space. These plumes, discovered by the Cassini spacecraft, are not merely beautiful spectacles. They offer tantalizing clues about the potential for life beyond Earth. Enceladus presents a unique environment that challenges the traditional understanding of where life can thrive. Most of our assumptions about life in the universe centered around warm, sunlit environments, places teeming with liquid water on the surface. However, Enceladus is a frozen world, its surface coated with thick ice. Yet beneath this icy crust lies a subsurface ocean, heated by the gravitational tug of Saturn. This geologic activity creates conditions that could support microbial life, despite the harsh outer shell. The geysers themselves are key to understanding this dynamic. When they erupt, they expel material from this subsurface ocean, including organic compounds, essential ingredients for life as we know it. The presence of these compounds challenges the notion that Earth-like conditions are a prerequisite for life. Instead, it opens up the possibility of life existing in environments previously considered inhospitable. Research into Enceladus prompts us to reconsider our definitions of habitability. As scientists analyze the plumes, they not only search for signs of life, but also seek to understand the complex chemistry that could unfold in extreme conditions. This shifting perspective invites us to explore other similar ocean worlds in our solar system, expanding our search for life to realms that were once thought uninhabitable. Europa, one of the most intriguing moons of Jupiter, is shrouded in mystery due to its icy crust that conceals an ocean beneath. This surface layer, composed primarily of ice, is believed to be covering a vast, salty ocean that could harbor conditions suitable for life. Scientists speculate that beneath the thick ice, the ocean may be in contact with Europa's rocky mantle, creating a chemically rich environment. Such interactions could mirror the conditions found around hydrothermal vents on Earth, where life thrives despite the absence of sunlight. The potential for a subsurface ocean raises profound questions about habitability. Europa is thought to possess more than twice the amount of water found on our planet. This gigantic ocean might be sheltering a diverse ecosystem, perhaps even microbial life. Drifting through this ocean are essential ingredients for life, such as organic compounds and energy sources. The idea that life may exist in such an extreme and hidden environment captivates scientists and the public alike, pushing us to reconsider where and how life might emerge in the universe. The surface of Europa is also of considerable interest. The ice appears to be fractured and ridged, suggesting tectonic activity that could allow nutrients and energy from the ocean below to surface, further supporting the possibility of life. Regular plumes of water vapor have also been detected, hinting at a dynamic exchange between the ocean and the outer environment. These plumes could provide a direct means of studying the ocean without having to drill through the thick ice. In the coming years, missions like the European Space Agency's Jupiter Icy Moons Explorer and NASA's Europa Clipper are set to deepen our understanding of this enigmatic moon. Through detailed observations and analysis, they aim to uncover secrets about Europa's ocean, its chemistry, and its potential for supporting life. With each new finding, Europa continues to captivate our imaginations, positioning itself as one of the most promising places in our solar system to search for extraterrestrial life. Mars, often regarded as Earth's closest neighbor, has fascinated scientists for decades, particularly in the search for life beyond our planet. Observations and studies of the Martian landscape reveal a dynamic history marked by changes in its climate and environment, which hold vital clues about the planet's potential for hosting life, both in the past and possibly in the future. Recent missions have uncovered evidence suggesting that liquid water once flowed freely on Mars. This conclusion is drawn from images depicting ancient riverbeds, lakebeds, and minerals that form in the presence of water. The presence of water is crucial because, as we understand, life as we know it depends on liquid water as a fundamental ingredient. The findings paint a picture of a once thriving environment that could have supported microbial life, making Mars a prime candidate in the quest to confirm if life existed beyond Earth. Moreover, the planet's current conditions are starkly different from those of its past. Today, Mars is a cold, arid world with a thin atmosphere, primarily composed of carbon dioxide. Understanding the mechanisms behind this dramatic shift helps scientists gauge how planetary environments can change over time. These changes inform not only the timelines for when life might have emerged, but also the resilience of any potential life forms that could survive in harsh environments. Looking to potential future missions, studying the changes on Mars helps shape human exploration endeavors. The insights gained from exploring how Mars has transformed over millennia allow scientists to identify safe habitats where microbial life may exist currently. By examining the remnants of water and geological features, we infer the planet's past while laying the groundwork for humanity's illustrious journey into the red planet, possibly unlocking the secrets of life as we delve into its depths. Venus, often dubbed Earth's twin due to its similar size and proximity, harbors a world of hidden potential beneath its seemingly hostile exterior. While the surface temperature averages around 450 degrees Celsius and the atmosphere is composed mostly of carbon dioxide, these extreme conditions might obscure the planet's intriguing possibilities. Scientists are increasingly curious about what lies beneath the thick clouds of sulfuric acid that blanket Venus, sparking interest in the potential for life and resource exploitation. One of the most captivating prospects for Venus is the existence of a more temperate environment in the upper atmosphere. At roughly 50 kilometers above the surface, temperatures can be surprisingly mild, hovering around 20 degrees Celsius. The volcanic plains and mountainous regions of Venus conceal vast deposits of valuable materials, which could be crucial for future space missions or even for mining operations as we venture further into our solar system. The geothermal activity that shapes the planet's surface may also provide insights into the processes that govern planetary geology, offering lessons that benefit our understanding of other celestial bodies. Finally, Venus serves as a fascinating laboratory for studying climate change. Its runaway greenhouse effect, which has rendered it inhospitable, raises important questions about our own planet's climate and atmospheric behavior. By examining Venus's climate history, scientists can gain critical insights into the potential futures of Earth and how we might mitigate similar fates. Thus, while Venus may seem like a forbidding world, it stands as a treasure trove of scientific opportunities waiting to be revealed. Magnetic fields play a crucial role in shaping the atmospheres of planets and subsequently their potential for habitability. At the heart of this relationship is the ability of a planet's magnetic field to protect its atmosphere from being stripped away by solar winds. Solar winds consist of charged particles emitted by the sun, traveling through space. Without a magnetic shield, these particles can collide with atmospheric molecules, eroding the atmosphere over time and making it difficult for a planet to retain the necessary conditions for life. For instance, Earth's magnetic field acts like a protective barrier against these energetic particles. It deflects the solar wind, allowing our atmosphere to remain intact. This stability provides the conditions that support liquid water on the surface, a fundamental ingredient for life as we know it. In contrast, planets like Mars, which have a weak magnetic field, have experienced significant atmospheric erosion. The loss of its atmosphere has led Mars to become a cold, dry world with very different conditions compared to Earth. Moreover, magnetic fields can also influence the chemical composition of a planet's atmosphere. By steering charged particles and preventing them from fostering harmful chemical reactions, a significant protective aspect of magnetic fields comes into play. This helps maintain the delicate balance of gases that can be essential for life, such as oxygen and carbon dioxide. The presence of a magnetic field is fundamental not just for retaining an atmosphere, but also for maintaining its composition. The interplay of magnetic protection, atmospheric stability, and chemical balance is vital for creating environments where life might arise or persist. As we continue to explore other planets, understanding the role of magnetic fields will be essential in our search for extraterrestrial life. The Kuiper Belt is a remarkable region at the edge of our solar system, extending from the orbit of Neptune out to about 50 astronomical units from the Sun. It is filled with small, icy bodies that are remnants from the early solar system. Understanding the Kuiper Belt helps scientists piece together the history and formation of our solar system, revealing the processes that shape the planets we know today. This belt hosts a multitude of objects, including dwarf planets like Pluto and Eris. These celestial bodies provide vital clues about the conditions that existed in the solar system during its infancy. By studying their composition and orbits, researchers can infer how these ancient materials have remained relatively unchanged for billions of years, serving as time capsules that hold secrets of the solar system's formation. Moreover, the Kuiper Belt marks a significant boundary between our solar system and interstellar space. It is thought to be a source of many short-period comets which originate from areas within the belt. As these comets venture toward the inner solar system, they reveal insights into the primordial materials that may have contributed to the emergence of life on Earth. As exploration continues, particularly through missions like New Horizons, which flew by Pluto, our understanding of the Kuiper Belt only deepens. Each new discovery challenges our previous notions and highlights a vast, dynamic outer solar system that is not just an edge, but a bustling environment with rich scientific significance. A black hole is an object in space with an incredibly strong gravitational pull, so strong that not even light can escape from it. This peculiar phenomenon forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. The result is a region in space where the gravitational forces overpower all others, creating an event horizon, the boundary beyond which nothing can return. But how do scientists detect something that emits no light? Astronomers do this by observing the effects of a black hole on surrounding matter. When a black hole pulls in gas and dust from a nearby star or the interstellar medium, it creates an accretion disk, a swirling mass of hot material. This material emits powerful radiation, particularly in the X-ray spectrum, as it spirals inward. By observing these emissions with specialized telescopes, scientists can infer the presence and behavior of a black hole. Another method of detection comes from the observation of gravitational waves. These ripples in space-time are produced by catastrophic events, such as merging black holes. When two black holes collide, they create waves that travel through the universe, stretching and compressing space as they pass. By detecting these waves, scientists gain insights into the properties of black holes, including their mass and spin. As our technology advances, so does our understanding of black holes. With missions like the Event Horizon Telescope, which captured the first image of a black hole's shadow in 2019, our quest to comprehend these mysterious objects continues to unfold. Each discovery deepens our understanding of these cosmic giants, igniting curiosity about their role in the universe. Black holes present a fascinating conundrum for physicists because they seemingly stretch the limits of our current understanding of the natural laws that govern the universe. At their core, black holes are regions in space where gravitational pull is so strong that nothing, not even light, can escape. This extreme manifestation of gravity becomes paradoxical when we consider that the laws of physics, particularly those formulated by Einstein and others, were developed without fully accounting for such entities. One of the key challenges that black holes pose is related to the concept of singularity. At the center of a black hole lies this singularity, a point where gravity becomes infinitely strong and space-time curves infinitely. Here, our equations break down, and we cannot describe what happens using our existing frameworks of physics. This discrepancy indicates that we may need a more comprehensive theory that reconciles general relativity, which describes gravity, with quantum mechanics, the framework for understanding the very small scales of particles and forces. Moreover, black holes raise profound questions about information. According to quantum mechanics, information is never truly lost, but when something falls into a black hole, it seems to disappear. This conundrum is famously known as the information paradox. It challenges the notion that all physical processes are reversible, pushing scientists to reconsider how we understand the fundamental nature of reality. Researchers are exploring ideas that could bridge these concepts, but the mystery remains largely unresolved. Finally, investigations into black holes are encouraging new theories and models which could lead to a unified understanding of the cosmos. As physicists delve deeper into these enigmatic structures, they are not just confronting black holes themselves, but are also probing the very nature of space, time, and existence. Each discovery inches us closer to a theory that could unlock the secrets of the universe, fundamentally changing how we view reality. The event horizon is a fundamental concept in the study of black holes, marking the boundary beyond which nothing can escape the gravitational pull of the black hole. Once an object crosses this threshold, it is effectively cut off from the rest of the universe. This makes the event horizon not just a physical boundary, but a point of no return, emphasizing the enigmatic nature of black holes. As such, understanding it is crucial for grasping how these cosmic giants behave. One of the most intriguing aspects of the event horizon is its relationship with light. Light, which travels at the fastest speed in the universe, cannot escape from within this boundary. This leads to the remarkable phenomenon that black holes appear black, since they do not emit light. Instead, they distort light from surrounding stars, an effect that can allow astronomers to infer the presence of a black hole and study its properties. For instance, as matter is pulled in, it heats up and emits radiation that can be observed with powerful telescopes, providing insights into the black hole's environment and activity. The event horizon also plays a vital role in our understanding of time and space. According to general relativity, as one approaches the event horizon, the gravitational effects become more intense. This leads to fascinating implications, such as time dilation, where time appears to slow down significantly for someone watching from a safe distance compared to an observer falling into the black hole. This strange interplay between time and gravity invites deeper questions about the fundamental laws that govern our universe. Moreover, the study of event horizons contributes to broader inquiries in physics, including the nature of information and its conservation. This is particularly relevant in discussions about what happens to information when it crosses the event horizon, which has captivated theoretical physicists for decades. As we continue to explore the mysteries of black holes, the event horizon remains a key focal point, revealing not only the secrets of these extraordinary objects, but also the underlying principles of our universe. Supermassive black holes, those mysterious giants at the centers of galaxies, form through a series of fascinating processes that unfold over cosmic timescales. The journey begins with the collapse of massive clouds of gas and dust in the early universe. These clouds, predominantly made of hydrogen and helium, undergo gravitational collapse, giving rise to the first stars. When these massive stars reach the end of their lifespans, they explode in supernovae, leaving behind dense remnants known as stellar black holes. As the universe continued to evolve, these stellar black holes could gradually merge with one another, creating more massive black holes. But there's more to the story. In the dense environments of early galaxies, these black holes could also accrete matter, essentially gathering surrounding gas, dust, and even stars, growing larger and larger. This process of accretion not only increases their mass, but can also produce intense energy emissions, which can light up the centers of galaxies and lead to the formation of quasars, some of the brightest objects in the universe. Over millions of years, the supermassive black holes at the centers of galaxies evolved through complex interactions with their surroundings. As galaxies collided and merged, their central black holes could also coalesce, forming even larger supermassive black holes. In fact, it's now believed that nearly every large galaxy, including our Milky Way, hosts one of these impressive entities. The exact mechanisms of their growth remain a subject of active research, with scientists exploring various scenarios, such as gas inflows, star mergers, and interactions with dark matter. Interestingly, the presence of supermassive black holes may also play a crucial role in the evolution of their host galaxies. The feedback from the energy released as matter spirals into these black holes can influence star formation rates and the overall growth of the galaxies themselves. This interconnectedness suggests that supermassive black holes are not just passive observers, but active players in the cosmic evolution happening all around them. Whichever way you look at it, their formation and growth not only answer questions about black holes, but also give insights into the history of galaxies and the universe as a whole. Gravitational waves are ripples in the fabric of space-time, generated by some of the most violent and energetic events in the universe. One of the key phenomena that produce these waves is the merger of black holes. When two black holes spiral toward each other and eventually collide, they release an immense amount of energy. This energy radiates away in the form of gravitational waves, which can travel across the universe, carrying information about the event that produced them. The detection of these waves allows scientists to gather invaluable data about the properties of the black holes involved in the merger. For example, gravitational waves can reveal the masses and spins of the black holes before they collide. This ability to measure such characteristics provides insight into the formation and evolution of black holes, helping researchers understand their origins and the environments from which they emerge. Moreover, the observed wave patterns provide context about the dynamics of the merger itself. The interaction between the black holes can be incredibly complex, and by analyzing the precise frequencies and amplitudes of the gravitational waves, scientists can infer details about how the black holes interacted in their final moments. This sheds light on questions like whether they formed from the same stellar population or if their merger was influenced by other factors, such as surrounding stars or gas. The collection of gravitational wave signals has opened a new window into astrophysical research. Each detection not only bolsters our understanding of black hole physics, but also enhances our knowledge of the universe's history. As we continue to observe more black hole mergers, we can piece together a more complete picture of these enigmatic objects and their roles in the cosmic landscape. Black holes wield immense influence over the galaxies that host them, shaping their structures and evolution in significant ways. At the center of most galaxies lies a supermassive black hole, often with a mass equivalent to millions or even billions of stars. These celestial giants not only attract surrounding matter through their staggering gravitational pull, but they also play a pivotal role in regulating star formation within the galaxy. As matter spirals into a black hole, it heats up and forms an accretion disk, emitting vast amounts of energy in the process. This energetic outflow can create powerful jets that shoot outwards, affecting the interstellar medium and dispersing energy far beyond the galaxy's core. These jets can trigger shock waves that compress nearby gas clouds, potentially sparking new star formations in regions previously devoid of activity. Thus, black holes can act as both destroyers and creators, influencing the birth and death of stars. Moreover, the presence of a supermassive black hole helps maintain the stability of the galaxy itself. As stars orbit around the black hole, they create a structured dynamic that can hold the galaxy together under gravitational influences. The interactions between stars and the black hole contribute to the overall movement and organization of the galaxy, creating a balance that prevents it from collapsing under its own weight. Interestingly, the growth of a black hole and the development of its host galaxy are intricately linked. As galaxies evolve over billions of years, their black holes tend to grow at similar rates to their stellar populations. This connection suggests a cosmic dance where the fate of stars and black holes are intertwined, highlighting their fundamental role in the architecture of the universe. Thus, black holes are not just cosmic anomalies, they are vital players in the grand narrative of galaxy formation and evolution. Hawking radiation, a concept proposed by physicist Stephen Hawking in the mid-70s, fundamentally reshaped our understanding of black holes. Traditionally, black holes were viewed as cosmic vacuum cleaners, drawing in everything around them and preventing anything from escaping, not even light. However, Hawking introduced the revolutionary idea that due to quantum mechanics, black holes can emit radiation. This radiation arises from virtual particles that spontaneously form near the event horizon. When one of these particles falls into the black hole, the other escapes, creating what we now call Hawking radiation. The implications of this phenomenon are profound. First, it suggests that black holes are not entirely black, but rather can slowly lose mass and energy over time. This leads to the groundbreaking notion that black holes might eventually evaporate entirely, eventually shrinking down to nothing. This process challenges the long-held belief that black holes are eternal entities, contributing to debates regarding the life cycle of these cosmic giants. Moreover, Hawking radiation raises significant questions about the fate of information that falls into a black hole. According to classical physics, once something passes the event horizon, it should be lost forever. However, quantum mechanics insists that information cannot be destroyed. This creates a paradox known as the black hole information paradox, sparking intense discussions and research in theoretical physics. If Hawking radiation allows for the escape of information, this could lead to revolutionary insights about the universe's fundamental laws. Lastly, the relationship between black holes and thermodynamics is redefined through Hawking's discovery. Black holes can now be viewed as thermodynamic objects possessing entropy, which aligns them with the laws of thermodynamics governing energy and information. This connection advances our understanding of the universe and inspires ongoing research into reconciling the principles of general relativity with quantum mechanics, potentially bringing us a step closer to a unified theory of physics. The concept of black holes as cosmic gateways often referred to as wormholes, is a fascinating area of theoretical physics. Black holes are regions in space where the gravitational pull is so strong that nothing, not even light, can escape them. This profound gravitational force arises from the collapse of massive stars after they exhaust their nuclear fuel. While black holes themselves are enigmatic and destructive, they also inspire theories about the interconnectedness of the universe, including the possibility of bridging distances via wormholes. Wormholes, on the other hand, are hypothetical passages through space-time that could create shortcuts between distant regions of the universe. According to some interpretations of Einstein's theory of general relativity, if a black hole could be connected to another point in space-time, it could function as a wormhole. This connection could allow matter or information to traverse vast cosmological distances in a fraction of the time it would typically take. However, the mathematics governing this scenario pushes the boundaries of our current understanding, raising more questions than answers. One of the significant challenges in considering black holes as wormholes lies in the concept of stability. Theoretical models suggest that for a wormhole to be traversable, it would require a special form of matter known as exotic matter. This substance would have negative energy density, which could keep the wormhole open against the crushing force of gravity, allowing safe passage. To date, exotic matter has not been observed, leaving the practicality of wormholes steeped in speculation. Moreover, if a traversable wormhole were to exist, it would not be without its challenges. It might be transient, unstable, and only open for a brief moment, making travel incredibly difficult, if not impossible. Despite these hurdles, the idea of utilizing black holes as gateways captivates the imagination and encourages further exploration into the nature of our universe. As we continue to unravel the mysteries of black holes and explore the intricacies of space-time, we may find that the universe holds surprises beyond our wildest dreams. The recent imaging of the black hole at the center of our Milky Way galaxy has shrouded it in layers of mystery and fascination. Known as Sagittarius A star, this black hole is about 4 million times the mass of our Sun, making it a titan within our cosmic neighborhood. While scientists have long theorized about supermassive black holes and their role in galactic evolution, the details of Sagittarius A star's behavior and structure continue to elude comprehensive understanding. One of the key mysteries pertains to the relationship between the black hole and the surrounding stars. Astronomers have observed that numerous stars spiral around Sagittarius A star at astonishing speeds. This movement suggests an incredibly massive object is influencing their orbits, yet much about the dynamics of these interactions remains unclear. How does Sagittarius A star exert its gravitational influence? And what does this reveal about the relationship between black holes and the formation of their surrounding stellar environment? Another intriguing aspect of Sagittarius A star is its relatively calm appearance when compared to other black holes, which are often associated with explosive energy outputs and jets of radiation. This calmer demeanor raises questions about what powers this black hole. Is it actively consuming matter at such a slow rate that it remains undetectable? Or is there a different mechanism at play here? The imaging has provided evidence of hot gas spiraling into the black hole, yet the precise nature of this accretion process remains an enigma. Finally, the study of Sagittarius A star and its mysteries also opens the door to thinking about the universe on larger scales. Understanding the nature of black holes like this one could lead to insights about the formation and evolution of galaxies, including our own. As researchers continue to analyze data from this monumental imaging project, we can only anticipate the revelations that might emerge, pushing the boundaries of our comprehension of the cosmos. The concept of an expanding universe emerged from observations made in the early 20th century, fundamentally changing our view of the cosmos. One of the earliest pieces of evidence came from the American astronomer Edwin Hubble, who discovered that galaxies are moving away from us in all directions. This was deduced by analyzing the light from distant galaxies, a phenomenon known as redshift. When light waves stretch, they shift toward the red end of the spectrum, indicating that the source is moving away. The farther away a galaxy is, the faster it appears to be receding, suggesting that the universe is expanding. Another pivotal piece of evidence comes from the cosmic microwave background radiation. This faint glow, uniformly detected across the sky, is a remnant of the early universe, specifically the period shortly after the Big Bang. Discovered in the 1960s, this radiation fills the universe and offers a snapshot of the cosmos when it was only about 300,000 years old. The uniformity and slight fluctuations in temperature of this radiation support the Big Bang theory and align with the idea of an expanding universe, as these variations hint at the seeds of structure that would grow into galaxies and clusters. Furthermore, the discovery of supernovae, particularly type Ia supernovae, has added depth to our understanding of expansion. Astronomers found that these stellar explosions serve as standard candles for measuring astronomical distances. Observations showed that distant supernovae are dimmer than expected, leading to the conclusion that the expansion of the universe is not just continuing, but accelerating. This unexpected acceleration has also led scientists to explore the concepts of dark energy, a mysterious force that seems to drive this expansion. All these pieces of evidence, Hubble's observations of redshifted galaxies, the cosmic microwave background radiation, and the behavior of distant supernovae, fit together to create a compelling picture of a universe that is not static but dynamic. The notion that space itself is stretching continuously has profound implications for our understanding of the cosmos and raises fundamental questions about its fate and the nature of the forces at play. The discovery of dark energy has profoundly reshaped our understanding of the universe. Before its revelation, the prevailing belief among scientists was that gravity, the force pulling matter together, would eventually slow down the expansion of the universe. However, observations in the late 20th century contradicted this notion, unveiling a startling reality. The universe is not only expanding, but that expansion is accelerating. This discovery left astronomers grappling with an unknown force, which we now call dark energy. Dark energy constitutes approximately 70% of the total energy density of the universe, making it a significant player in cosmic dynamics. This mysterious substance creates a repulsive effect, counteracting the attractive force of gravity on a large scale. The implications of this are enormous. It suggests that the fate of the universe is no longer a gradual slowdown leading to a potential collapse, but rather a continued expansion that may eventually lead to a cold, dark cosmos. If dark energy remains constant over time, we could be witnessing a future where galaxies drift away from one another, stretching the fabric of the universe to its limits. Moreover, dark energy has sparked a surge of questions about the fundamental nature of the universe itself. Scientists are exploring whether this force is a constant, a varying field, or even a manifestation of a deeper, more exotic physical principle. Various theories have emerged, from modifications of gravity to the existence of additional dimensions. Each hypothesis opens up new avenues for research, challenging our knowledge of physics and driving innovation in cosmological studies. As scientists delve deeper into dark energy, they continue to refine our understanding of the cosmos. This exploration not only enhances our grasp of the universe's current state, but also informs predictions about its ultimate fate. Ultimately, the discovery of dark energy has not just added a layer of complexity to astrophysics, it has ignited a quest to unravel one of the most profound mysteries of existence, capturing the imaginations of scientists and enthusiasts alike. The cosmic microwave background, often abbreviated as CMB, plays a pivotal role in our understanding of the universe's history. This faint glow of light fills the universe and is a relic from the early stages of cosmic evolution, specifically from a time when the universe was just a hot and dense soup of particles. Approximately 388,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine into hydrogen atoms, allowing light to travel freely. This moment marked the release of the CMB. By analyzing the tiny variations in temperature across the CMB, researchers can infer information about the distribution of matter in the early universe. These fluctuations are essential clues that have helped shape our understanding of how galaxies formed and evolved over billions of years. Furthermore, the CMB serves as a cornerstone for Big Bang cosmology, providing strong evidence that supports the theory. Its nearly uniformity across the sky suggests a level of homogeneity in the early universe, which is fundamental to many models of cosmic evolution. Scientists use the data from the CMB to refine their measurements of fundamental parameters of the universe, including its age, composition, and the rate of its expansion. These insights are crucial for piecing together the complex tapestry of cosmic history. The cosmic microwave background is not just a remnant of the early universe. It is a powerful tool for cosmologists. By studying this ancient light, we uncover the underlying principles governing the cosmos and deepen our understanding of its vast and intricate history. The CMB continues to inspire new questions and discoveries, revealing the universe's secrets layer by layer, much like peeling back the petals of a cosmic flower. To understand the rate of universal expansion, scientists rely significantly on a concept known as the redshift of light from distant galaxies. When astronomers observe the light emitted from these galaxies, they find that it is shifted toward longer wavelengths, a phenomenon called redshift. This occurs due to the Doppler effect, which suggests that as galaxies recede from us, their light is stretched. By measuring how much the light has shifted, scientists can determine how fast a galaxy is moving away from Earth. Once they have established that galaxies are moving away from us, scientists can utilize Hubble's law, which posits a direct relationship between a galaxy's distance and its velocity. In simple terms, the farther away a galaxy is, the faster it appears to be moving. Edwin Hubble, an American astronomer, first discovered this relationship in the early 20th century and set the stage for our understanding of a continuously expanding universe. By plotting the redshift data against distances to various galaxies, scientists create what's known as the Hubble diagram, illustrating this extraordinary relationship. Additionally, astronomers measure the cosmic microwave background radiation, which is the afterglow of the Big Bang. This radiation provides crucial evidence about the universe's early state and its continuing expansion. By studying this relic radiation, scientists can estimate the rate of expansion known as the Hubble constant. Various techniques, like observations of supernovae and gravitational lensing, also refine the accuracy of these measurements, contributing to our understanding of the universe's dynamics. Interestingly, research has revealed that the rate of expansion is not constant. Recent studies suggest that the universe is expanding at an accelerating rate, implying the presence of a mysterious force known as dark energy. This discovery has not only reshaped our understanding of cosmology, but has also opened up new avenues of inquiry into the nature of the universe itself and the fundamental forces at play. As we continue to observe and measure the cosmos, the quest to fully grasp its expanding nature unfolds, inviting curiosity and awe in equal measure. The discovery that our universe is accelerating in its expansion has profound implications for its ultimate fate. As galaxies move away from each other at an increasing pace, it challenges our understanding of cosmic dynamics and fate. This acceleration suggests that the universe is not only expanding, but that this expansion is driven by a mysterious force known as dark energy. Dark energy makes up about 70% of the universe, yet its true nature remains one of the great mysteries of modern cosmology. As the universe continues to expand faster, the structure of cosmic existence will change dramatically. Stars will eventually exhaust their nuclear fuel, leading to their demise. Existing galaxies will drift further apart, and those in our local group may eventually become isolated in a vast, dark space. Over immense periods, the visible universe may consist solely of the remnants of old stars and black holes, an eerie whisper of the vibrant cosmos we observe today. The ultimate fate of the universe could lead to what is known as the Big Freeze. In this scenario, as galaxies recede beyond our observable limit, the night sky will become increasingly dark and empty. Eventually, stars will burn out, and significant cosmic events will grow rare. This gradual cooling will erase the vibrant cosmos we experience, leaving behind a cold, dark void where only the most massive objects, like black holes, might linger for billions of years, slowly dying away through processes like Hawking radiation. An alternative scenario is the Big Rip, where the accelerated expansion continues to intensify. In this outcome, the fabric of space-time itself would tear apart. Galaxies, stars, and even atoms could be ripped asunder in the face of an unstoppable cosmic expansion, culminating in a singularity where ordinary concepts of space and time cease to exist. While these theories about the universe's fate are grounded in current understanding, they highlight just how much we still have to learn about the cosmos and its expansive future. Galaxy clusters serve as monumental cosmic laboratories, allowing scientists to probe the intricate tapestry of the universe's large-scale structure. These clusters are composed of hundreds to thousands of galaxies bound together by gravity, forming some of the largest structures we observe in the cosmos. Their immense mass not only gives rise to strong gravitational fields, but also influences the motion of the surrounding galaxies and the distribution of dark matter in the universe. By studying the formation, distribution, and dynamics of galaxy clusters, astronomers can glean valuable information about the overall architecture of the universe. The locations and clumping patterns of these clusters act as markers, shedding light on the underlying gravitational forces at play, which are a mixture of both visible matter and the elusive dark matter. This understanding is crucial for piecing together how structures evolve over billions of years and how they relate to cosmic inflation and the expansion of the universe itself. Additionally, galaxy clusters are pivotal in understanding the role of dark energy, a mysterious force thought to be driving the accelerated expansion of the universe. Observations of clusters can indicate how quickly they form and grow, which in turn helps researchers refine their models of cosmic evolution. The way clusters gather and interact provides clues about the balance of forces that shape the universe and continues to influence its destiny. Engaging with these colossal structures enriches our comprehension of fundamental cosmological questions. Each detected cluster from various surveys acts as a beacon, revealing the universe's history and the dynamics that drove its expansion. Ultimately, the study of galaxy clusters reveals not just the current state of the universe, but also unravels the narrative of its origins and fate, offering a glimpse into the cosmic community we inhabit. Cosmic voids, those vast expanses of space, nearly devoid of galaxies, offer a unique window into understanding the universe's composition and evolution. These enormous regions can stretch hundreds of millions of light-years across and typically contain only a few galaxies, in stark contrast to the densely packed structures found in galaxy clusters. By studying these voids, scientists can glean insights into dark energy, dark matter, and the overall distribution of matter in the cosmos. One of the most fascinating aspects of cosmic voids is their relationship with dark energy, the mysterious force believed to be driving the accelerated expansion of the universe. As voids grow larger over time, they highlight areas where gravity is weak, allowing us to observe how matter and energy have evolved since the Big Bang. These empty spaces act like a cosmic canvas, revealing how the large-scale structure of the universe has been shaped by the interplay between gravity and the expansion driven by dark energy. Moreover, the composition of voids can inform our understanding of dark matter. While voids are mainly empty, they still contain small amounts of baryonic matter, such as gas and dust. By studying the characteristics of these materials within voids, scientists can draw conclusions about the density and distribution of dark matter, an unseen substance that makes up about 27% of the universe. The structure of voids can reflect the gravitational influence of dark matter, providing clues to its role in cosmic evolution. Exploring cosmic voids is like examining the quiet parts of a symphony, where understanding the absence of sound can reveal profound truths about the music itself. The study of these vast emptiness not only enriches our understanding of cosmic structures, but also enhances our knowledge of the fundamental components of the universe itself, bridging the gap between visible matter and the enigmatic forces that govern the cosmos. The scale of the universe presents a profound challenge to human perception and understanding. To put it simply, the universe is vast beyond what most of us can truly comprehend. When we look up at the night sky, we see stars that are not just millions, but billions of light years away. This distance is unfathomable for our everyday experiences, where most of our interactions happen within a few miles or kilometers. The concept of size and distance in the cosmos defies our intuitive sense of scale, compelling us to rethink our place in the universe. One of the most striking aspects is the sheer number of celestial bodies. Researchers estimate there are over 100 billion galaxies in the observable universe, each containing millions to trillions of stars. To grasp that number, consider that it vastly exceeds the total number of grains of sand on Earth. This staggering reality can inspire a sense of humility as we realize that we are just one small planet orbiting an ordinary star in an unremarkable galaxy. The scale of the universe invites us to rethink human significance and our role in the cosmic narrative. Furthermore, the vastness creates challenges in communication and understanding. Think about how we describe distances in space. An example is the light year, which measures how far light travels in 1 year. This unit alone can lead to confusion, as the distance between us and even our nearest star, Proxima Centauri, is over 4 light years. This means that the light we see today left that star over 4 years ago. For many, it's hard to wrap one's mind around the fact that we are viewing the past when we look at stars, introducing layers of complexity into our understanding of time and space. Ultimately, the scale of the universe compels us to rely on scientific tools and methods to explore and comprehend it. Telescopes, satellites, and advanced simulations are essential in piecing together the vast puzzle of the cosmos. As we continue to push boundaries in our exploration of the universe, each discovery contributes to a growing tapestry of knowledge. This ongoing journey not only expands our scientific understanding, but deepens our appreciation for the mystery and grandeur of the universe, reminding us of the endless questions still to explore. Dark matter is one of the most intriguing mysteries in cosmology. It is an invisible substance that does not emit or interact with electromagnetic radiation, which means we cannot see it directly using telescopes. Yet, it is estimated to make up approximately 27% of the total mass and energy content of the universe. This elusive material plays a crucial role in anchoring galaxies and clusters, influencing their formation and movement through gravitational interaction. To understand the significance of dark matter, we must consider how galaxies behave. Observations reveal that galaxies rotate at surprisingly high speeds, much faster than what can be explained by the visible matter they contain. If we only accounted for stars, gas, and dust, galaxies would tear themselves apart. The presence of dark matter provides the additional gravitational pull needed to hold these spinning masses together. Without it, the cosmos would look markedly different, with galaxies potentially failing to form or being torn apart. Further evidence of dark matter's existence comes from the cosmic microwave background radiation. This faint glow left over from the Big Bang shows patterns that reflect how matter, both visible and dark, was distributed in the early universe. The way light bends around massive objects due to gravity, a phenomenon known as gravitational lensing, also strongly supports the existence of dark matter, as it reveals more mass than can be accounted for by just the visible stars and galaxies. Despite our growing awareness and understanding of dark matter, its exact composition remains unknown. Various candidates have been proposed, including weakly interacting massive particles, or WIMPs, but no definitive detection has been made so far. Exploring this cosmic enigma not only deepens our understanding of the universe's structure, but also challenges our perceptions of reality itself, pushing the boundaries of modern physics. The existence of dark matter is one of the most fascinating puzzles in contemporary astrophysics. Scientists infer its presence primarily through its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. For instance, when astronomers observe galaxies, they notice that the stars at the edges are rotating at much higher speeds than would be expected based on the visible mass alone. This discrepancy suggests that an unseen mass, which we refer to as dark matter, is exerting gravitational influence on these stars. One of the most compelling pieces of evidence comes from studying galaxy clusters. When scientists look at clusters, they calculate the mass based on the visible galaxies and hot gas within them. Yet, the observed gravitational effects are far greater than the mass of the visible matter. This implies that there must be a significant amount of additional, unseen matter present, again pointing to dark matter as a key player. Moreover, scientists utilize a phenomenon known as gravitational lensing. This occurs when a massive object, such as a galaxy cluster, bends the light from objects behind it. By measuring the degree of this bending, astronomers can estimate the total mass of the cluster, including the mysterious dark matter. This method has revealed that dark matter constitutes about 26% of the universe, in stark contrast to the mere 5% that is made up of ordinary matter. Furthermore, simulations of the universe's formation and evolution reveal that dark matter plays a crucial role in the growth of cosmic structures. These simulations match up well with observations of the distribution of galaxies across vast distances. While dark matter remains elusive and undetectable through conventional means, its gravitational effects create a rich tapestry of evidence that continues to intrigue and challenge scientists in their quest to understand the true nature of the universe. Dark matter is one of the universe's greatest mysteries, making up about 27% of its total mass and energy. Despite its prevalence, it remains elusive to direct detection. Scientists have launched several ambitious experiments to uncover its secrets. One of the most notable initiatives is the Large Underground Xenon Experiment, or LUX-ZEPLIN, located deep underground in South Dakota. This setup aims to spot the faint interactions of dark matter particles with normal matter using a tank filled with liquid xenon and advanced detection technology. Another intriguing effort is the cryogenic rare events search with superconducting thermometers, commonly known as CREST. Stationed in an underground lab in Italy, CREST is designed to catch the telltale signals of dark matter by detecting tiny amounts of heat produced when a dark matter particle might collide with a nucleus of a calcium-tungsten crystal. By using sophisticated sensors, researchers hope to measure these minuscule temperature changes with extraordinary precision. Moving beyond these labs, experiments like PANDAX in China and the Xenon-T experiment, which also uses liquid xenon, are actively searching for signs of dark matter interactions. Each of these experiments is uniquely situated in deep underground facilities to shield them from cosmic rays and other background noise that could obscure signals from potential dark matter detections. By utilizing different technologies and detection methods, these experiments are creating a more comprehensive picture of what dark matter might be. As scientists continue to innovate and collaborate, the quest to directly detect dark matter remains a vibrant and hopeful frontier in modern physics. With each experiment, our understanding edges closer, reminding us how much there is yet to learn about the universe and the unseen forces that govern it. The coming years may hold the key to transformative discoveries that could reshape our comprehension of the cosmos. Dark matter and ordinary matter are both essential components of the universe, yet they possess strikingly different characteristics. Ordinary matter, which makes up everything that we see around us, like stars, planets, and living organisms, consists of atoms. These atoms are made up of protons, neutrons, and electrons, which interact with one another through fundamental forces. This interaction leads to the formation of visible structures and ultimately the complexity of life as we know it. In contrast, dark matter eludes direct detection as it does not emit, absorb, or reflect light, making it invisible to our telescopes and scientific instruments. While we cannot see dark matter, its presence is inferred from its gravitational effects on ordinary matter. For instance, astronomers have observed that galaxies rotate at such speeds that they should be flying apart if only ordinary matter were influencing their motion. The additional gravitational pull exerted by dark matter, which surrounds these galaxies, explains why they remain intact. In the grand scheme of the cosmos, dark matter plays a crucial role in the formation and structure of the universe. It is estimated that about 25% of the universe is composed of dark matter, while ordinary matter only makes up roughly 5%. This means that a significant portion of the matter in the universe is entirely beyond our sight and comprehension, yet governs the behavior of galaxies and clusters on a cosmic scale. Understanding dark matter is one of the most significant challenges in modern astrophysics. Researchers continue to explore its properties and search for potential candidates, with some hypothesizing that it may consist of exotic particles that differ fundamentally from the particles of ordinary matter. As scientists gather more data and enhance their detection techniques, the mystery surrounding dark matter continues to intrigue and inspire new generations of cosmologists. Dark matter, though invisible and intangible, plays a pivotal role in shaping the universe, especially in the formation of galaxies. It comprises about 26% of the universe's total mass and energy. Despite being undetectable by conventional means, scientists infer its presence through its gravitational effects on visible matter, such as stars and gas. This unseen mass serves as the scaffolding around which galaxies and galaxy clusters form. As the universe began to cool and expand after the Big Bang, regions of slightly higher density emerged amid a sea of a nearly uniform distribution of matter. Dark matter, concentrated in these regions, provided the gravitational pull needed to attract nearby matter. This process led to the clumping of gas, dust, and stars, gradually forming the first galaxies. The gravitational influence of dark matter is so significant that it acts like a cosmic glue, holding galaxies together and preventing them from flying apart. As galaxies evolved, dark matter continued to play a crucial role in their dynamics. It not only helped in the initial formation, but also supported ongoing processes like star formation and galaxy collisions. The presence of dark matter alters the rotation speeds of galaxies, which is observable through the way stars and gas circulate around the galactic center. This discrepancy between visible mass and gravitational influence serves as key evidence for dark matter's existence. Researchers also believe that dark matter influences the large-scale structure of the universe. It forms a vast, web-like framework that dictates how galaxies cluster and interact with one another. Understanding dark matter is essential for piecing together the history of the universe and predicting the future of galaxy formation, making it one of the most essential components of modern cosmology. Dark matter plays an essential role in the formation and behavior of galaxies throughout the universe. While it remains invisible and undetectable by conventional means, its presence is inferred from various astronomical observations. Essentially, dark matter is believed to make up about 26% of the total mass-energy content of the cosmos, which is substantial. It does not emit, absorb, or reflect light, meaning it can only be identified through its gravitational influence on visible matter, such as stars and gas within galaxies. One of the primary effects of dark matter is its influence on the motion of galaxies. When astronomers study the rotation curves of spiral galaxies, they notice that the outer regions of these galaxies rotate at unexpectedly high speeds. According to the laws of physics, particularly Newton's law of gravitation, these outer stars should move more slowly than those nearer to the center. The persistent high speeds suggest that there is additional mass-exerting gravitational force, the elusive dark matter. This additional mass operates in a halo surrounding galaxies, providing the extra gravitational pull needed to maintain the observed speeds. In terms of structure, the presence of dark matter is instrumental in galaxy formation. Early in the universe's history, tiny fluctuations in density served as seeds for the formation of cosmic structures. Dark matter clumped together under the influence of gravity, creating a framework around which ordinary matter coalesced. As gas fell into these gravitational wells, it cooled and formed stars, ultimately leading to the diverse galaxy structures we see today. Without dark matter, the current arrangement and variety of galaxies would likely be vastly different. Moreover, studies of galaxy clusters have revealed how dark matter affects their dynamics. The significant gravitational attraction of dark matter holds these clusters together, countering the effects of the outward pressure from the hot gas that fills them. This balance shapes the organization of galaxies within clusters, influencing their interactions and trajectories over cosmic time. Understanding dark matter not only helps us to unravel the mysteries of galaxy formation and evolution, but also deepens our understanding of the universe as a whole. Dark matter, which makes up about 25% of the universe, remains one of the greatest mysteries in cosmology. Though invisible and undetectable by current telescopes, its presence is inferred through gravitational effects on visible matter, such as galaxies and galaxy clusters. Scientists have proposed several theories about what dark matter could be. However, no single theory has been universally accepted. One leading theory suggests that dark matter is composed of weakly interacting massive particles, or WIMPs. WIMPs are hypothetical particles that would interact only through the weak nuclear force and gravity, making them incredibly elusive. Researchers hope to detect these particles using specialized underground detectors, as they would create very faint signals when they collide with ordinary matter. Despite extensive search efforts, including large-scale experiments around the world, WIMPs have yet to be observed directly. Another intriguing possibility points to axions, lightweight particles that could also account for dark matter. Axions are predicted by certain theories in particle physics, notably within the context of quantum chromodynamics. Their unique properties may allow them to form a different type of dark matter, known as axion clouds, which could manifest as a specific type of wave. If axions exist, they might explain not just dark matter, but also some unresolved puzzles in physics, such as why the strong force behaves the way it does. Lastly, some theories even entertain the idea of primordial black holes formed in the early universe, which could contribute to the dark matter density. These black holes would range in size from a few times the mass of our Sun to potentially millions of solar masses. Each of these hypotheses reveals a different aspect of the universe's hidden structure and composition. As scientists continue to refine their telescopes and experiments, the quest to uncover the true nature of dark matter remains a fascinating frontier in our exploration of the cosmos. The quest to discover extraterrestrial life has seen groundbreaking advancements in technology, shaping how we explore the universe. One of the most significant developments is the enhancement of space telescopes. Instruments like the James Webb Space Telescope have opened a new frontier in astronomy. Able to peer into distant exoplanet atmospheres, this advanced technology can analyze the composition of gases, searching for biosignatures, chemical indicators that life as we know it might exist. In addition to space telescopes, improvements in artificial intelligence and machine learning allow scientists to process vast amounts of data more efficiently than ever. With thousands of potential exoplanets catalogued, AI systems can sift through information from past observations and predict which worlds possess conditions conducive to life. This data-driven approach not only streamlines our search, but uncovers new insights that might have gone unnoticed using traditional methods. Moreover, advancements in robotic exploration play a crucial role in our search for life beyond Earth. Rovers and landers, such as Perseverance on Mars, are equipped with sophisticated instruments for chemical analysis. These machines collect samples and conduct experiments, testing the soil for organic compounds. Such technology enables a deeper understanding of other worlds, providing clues about their potential habitability. Finally, the development of communication technologies has transformed our ability to explore the cosmos. Projects such as the Search for Extraterrestrial Intelligence, or SETI, utilize powerful radio telescopes to listen for signals from intelligent civilizations. Innovations in signal processing make it possible to filter out noise and identify potential communications from distant stars, making the dream of cosmic connection more attainable than ever before. As technology continues to evolve, our prospects for discovering extraterrestrial life grow ever brighter. Astrobiologists are continuously pushing the boundaries of our understanding of life beyond Earth, and identifying potentially habitable exoplanets is a crucial part of this quest. It all begins with the discovery of exoplanets, planets orbiting stars outside our solar system. Scientists use various methods to detect these distant worlds, including the transit method, where they measure the dimming of a star's light as a planet passes in front of it, and the radial velocity method, which observes the wobble of a star caused by the gravitational pull of an orbiting planet. Once exoplanets are identified, astrobiologists focus on several key factors that contribute to a planet's habitability. The most significant of these is the planet's location within the so-called habitable zone, often referred to as the Goldilocks zone. This zone is just the right distance from a star, not too hot and not too cold, for liquid water to exist on the planet's surface. Since water is essential for life as we know it, this zone is a primary target in the search for potential habitats. Furthermore, scientists examine the characteristics of the planets themselves, including their size, composition, and atmosphere. For instance, rocky planets similar to Earth are considered more promising than gas giants for sustaining life. Researchers rely on powerful telescopes like the Hubble Space Telescope and the recently launched James Webb Space Telescope to analyze the atmospheres of these exoplanets. By studying light spectra, they can identify the presence of gases like oxygen, methane, and carbon dioxide, which could hint at biological processes. In addition to these criteria, ongoing advancements in technology and methods improve the efficiency of finding and studying these exoplanets. As we learn more about the stars they orbit, like their age, stability, and the type of radiation they emit, our understanding of a planet's potential environment deepens. This holistic approach not only enhances our search for distant worlds that might harbor life, but also gets us one step closer to answering the profound question of whether we are truly alone in the universe. Extremophiles, those marvelous organisms inhabiting Earth's most extreme environments, offer invaluable insights into the possibility of life beyond our planet. These resilient beings thrive in conditions that would be hostile or even lethal to most life forms. They can be found in the boiling waters of hydrothermal vents, the freezing temperatures of Antarctica's ice, and even in the acidic lakes of Chile. By studying these organisms, scientists are learning how life can adapt to survive where the conditions are anything but ordinary. One significant lesson from extremophiles is their biochemical versatility. Many of these organisms have unique adaptations that allow them to endure extreme temperatures, pressures, and pH levels. For instance, some microbes produce proteins called heat shock proteins, which help them withstand high temperatures. Others have developed membranes that remain stable even in extreme acidity or salinity. These adaptations suggest that life can potentially exist in a variety of environments across the cosmos, expanding the types of extraterrestrial settings where life might thrive. Furthermore, extremophiles also illuminate how life may emerge in environments previously thought uninhabitable. For example, organisms found in permafrost or deep under the ocean demonstrate that life can persist in isolation for millions of years. This persistence hints at possible life forms on other planets or moons, such as Europa or Enceladus, where liquid water and energy sources exist beneath icy crusts. The idea that life can survive in such secluded locales encourages scientists to broaden their search for extraterrestrial biology. The study of extremophiles not only reshapes our understanding of life's potential on Earth, but also transforms our outlook on the universe. They serve as a mirror reflecting the resilience and adaptability of life, reminding us that, irrespective of the harshness of an environment, the potential for life still exists. As we continue to explore our solar system and beyond, these remarkable organisms inspire scientific inquiries that may one day lead us to discover life beyond our blue planet. The study of exoplanet atmospheres is revolutionizing our approach to the search for extraterrestrial life. As scientists discover more exoplanets, worlds that orbit stars outside our solar system, they are increasingly focused on analyzing the compositions of these distant atmospheres. This involves studying the light from a star as it passes through a planet's atmosphere during a transit, revealing crucial information about the gases present. By identifying elements like oxygen, carbon dioxide, and methane, researchers can begin to understand whether a planet might support life as we know it. One key concept in this exploration is the idea of biosignatures, which are indicators that life may exist on a planet. For instance, the presence of methane alongside oxygen could suggest biological activity, since these two gases tend to react chemically and would not coexist for long unless replenished. The detection of such a combination could be a compelling sign that life is influencing the atmosphere. Researchers are developing sophisticated telescopes and instruments, such as the James Webb Space Telescope, to help in the hunt for these life signs across various atmospheres. Moreover, the study of these atmospheres is not limited to finding Earth-like planets. Understanding how different gases interact and what environments they create opens up a broader perspective on habitability. Researchers are considering the atmospheres of gas giants and icy worlds as potential candidates for life, expanding the types of environments that may host living organisms in forms we have yet to imagine. This shift in thinking is allowing scientists to entertain a variety of biosignatures that weren't previously considered. Ultimately, the exploration of exoplanet atmospheres is guiding us toward a deeper understanding of life's potential in the universe. Each new discovery peels back layers of mystery surrounding our cosmic neighborhood, prompting exciting questions. As we refine our abilities to analyze these distant worlds, the possibility of uncovering signs of life elsewhere becomes more tangible, reshaping our understanding of life in the cosmos and our place within it. As we explore the possibilities of life beyond Earth, our solar system presents several intriguing candidates. The most promising among these are Europa, a moon of Jupiter, and Mars, our closest planetary neighbor. Additionally, Enceladus, a small moon of Saturn, has also gained attention for its potential to harbor life. Each of these locations features conditions that raise the possibility of life existing in some form. Europa captivates scientists with its icy surface, beneath which lies a vast ocean of liquid water. This ocean is believed to be in contact with the moon's rocky mantle, creating an environment where chemical reactions essential for life could occur. The surface of Europa is cracked and scarred, suggesting geological activity and the potential for hydrothermal vents similar to those found on Earth, which sustain unique ecosystems. Mars has long been a focal point in the search for extraterrestrial life. Evidence suggests that liquid water once flowed on its surface, carving out valleys and riverbeds. Current missions are focused on finding signs of past life by investigating ancient lakebeds and polar ice caps. The discovery of seasonal methane emissions on Mars adds another layer of intrigue. As on Earth, methane is often produced by biological processes. Then there's Enceladus, where geysers erupt from the moon's southern pole, spewing water vapor and organic compounds into space. These plumes suggest that beneath Enceladus's icy crust, a subsurface ocean may also exist. Analyzing the composition of these eruptions could provide vital clues about the ingredients necessary for life. As we advance our exploration techniques, our understanding of these intriguing worlds may soon reveal just how common life could be within our celestial neighborhood. The quest for microbial life on Mars and beyond is an exciting frontier in space exploration, driven by the pursuit of understanding whether we are alone in the universe. Scientists employ a combination of advanced technology, ingenious engineering, and collaboration across disciplines to seek out signs of life or its building blocks on other planets and moons. A prime candidate for this investigation is Mars, where evidence suggests that liquid water once flowed, creating an environment that could have supported microorganisms. To search for life, scientists rely on robotic missions equipped with sophisticated instruments. Rovers like Perseverance are designed to collect samples of Martian soil and rock, analyzing their chemistry in real time. These rovers use a suite of tools to detect organic molecules, which are essential for life as we know it. They also utilize cameras and spectrometers to capture detailed information about the Martian surface and atmosphere, searching for biosignatures, indicators that living things once existed there. Beyond Mars, the search broadens to the icy moons of the outer solar system, such as Europa and Enceladus. Scientists believe these moons may harbor subsurface oceans beneath their icy crusts. To explore these worlds, missions like the upcoming Europa Clipper will help identify the chemical signatures of potential life forms. These missions aim to analyze the surface and capture data about the moon's ocean compositions, looking for the necessary ingredients for life, such as water, carbon, and energy sources. The exploration does not stop with Mars and its moons. Scientists are also investigating exoplanets, planets outside our solar system, in the habitable zones where conditions might be just right for life. Telescopes like the James Webb Space Telescope provide unprecedented views into distant worlds, analyzing their atmospheres for signs of water, methane, and other chemicals associated with life. This comprehensive strategy of exploring both nearby planets and distant exoplanets keeps the dream of finding microbial life very much alive in the scientific community. The discovery of extraterrestrial life would profoundly impact humanity in ways we can only begin to imagine. First and foremost, it would fundamentally alter our understanding of life itself. For centuries, we have pondered the origins of life on Earth and whether we are alone in the universe. Finding extraterrestrial beings, whether simple microbial organisms or advanced civilizations, would broaden our definition of life and our place in the cosmic landscape. Moreover, the implications would extend into philosophical and ethical realms. Consider the questions that would arise about the nature of consciousness, the morality of interacting with other intelligent beings, and how we view ourselves in relation to all other life forms. Our religious and cultural narratives might be challenged, compelling us to rethink ideas that have shaped societies for millennia. The redrawing of paradigms could inspire unity as humanity reflects on shared existence in a vast universe filled with possibilities. On a scientific front, the discovery would ignite a renaissance in research and exploration. Scientists would ramp up their efforts in astrobiology, planetary science, and even astronomy, seeking to understand not only the forms of extraterrestrial life, but also how these organisms survive and thrive in environments vastly different from Earth. This knowledge could provide insights into our own biological processes and ecosystems, potentially leading to advancements in medicine, agriculture, and environmental preservation. Finally, the discovery of extraterrestrial life would spark discussions on technological and communicative advancements. If we were to establish contact with an intelligent civilization, the potential exchange of knowledge could propel scientific advancements beyond our current imagination. Humanity would have to navigate the complexities of interstellar diplomacy, leading to questions about cooperation, conflict, or mutual benefit on a scale we have never faced before. The conversation around extraterrestrial life would open a new chapter in human history, compelling us to reconsider not just who we are, but who we aspire to be in a universe full of secrets yet to be unveiled. The quest to communicate with intelligent extraterrestrial civilizations has fascinated scientists and dreamers alike for decades. At the heart of this pursuit lies the understanding of how such communication might transcend the vast distances and differences between species. One of the most popular methods is the use of radio signals, which can carry information across light years without requiring physical travel. The breakthrough was initiated by pioneering projects like the Search for Extraterrestrial Intelligence, or SETI, which involves scanning the skies for radio signals that defy natural explanations. One intriguing concept is the use of electromagnetic waves to send messages into space. By broadcasting focused signals towards star systems that could host habitable planets, we might someday reveal our presence to intelligent beings out there. However, this approach brings challenges, such as ensuring that our signals can be understood and deciphered by civilizations potentially very different from our own. The creation of universal mathematical principles or the encoding of information within a recognizable framework, such as prime numbers, are ways to make communication more universally interpretable. Another avenue involves the idea of beacons or spacecraft that could carry messages. These could be sent to neighboring star systems or even farther away, intended to remain in orbit or on a trajectory that allows them to reach extraterrestrial civilizations. The messages encoded in these beacons could contain information about humanity, our culture, our history, and our understanding of the cosmos. This approach emphasizes the idea that contact might not be instantaneous, but rather a long-term endeavor requiring patience and thoughtful planning. In addition to technology, the challenge also lies in forming a common language. Just as humans have developed diverse languages and symbols based on culture and experience, extraterrestrial life may possess entirely different concepts and methods of communication. The study of xenolinguistics, potential languages of alien civilizations, opens a treasure chest of possibilities for how we might decode messages from the stars. In exploring these myriad approaches, the hope remains that one day we will be able to bridge the gap, fostering understanding across the unimaginable expanse of the universe. The formation of galaxies is a fascinating journey that begins with some of the smallest and simplest particles in the universe. Shortly after the Big Bang, the universe was primarily composed of hydrogen and helium atoms, along with a few trace elements. These primordial particles floated in a vast expanse of space, where gravity began to play a crucial role. Over millions of years, slight irregularities in the density of these particles caused some areas to attract more matter. This gravitational attraction laid the groundwork for the first structures in the universe. As regions of gas and dust accumulated more material, they started forming clumps called protogalaxies. These protogalaxies were not yet fully formed galaxies, but they were vital stepping stones. As they gathered more gas, their gravitational pull increased, leading to further accumulation of matter. The process resembled a cosmic snowball effect. The more mass a protogalaxy acquired, the stronger its gravity became, accelerating its growth. Eventually, these protogalaxies continued to collide and merge with one another, forming larger, cohesive structures. During these encounters, tremendous amounts of energy were released, igniting new stars and triggering bursts of star formation. This phase of galactic evolution was a hotbed of activity, with young stars illuminating the darkness of the universe and enriching their surroundings with heavier elements forged in their cores. Over billions of years, these processes coalesced to create the diverse array of galaxies we see today. Today, galaxies come in various shapes and sizes, from spirals like our Milky Way to massive elliptical galaxies. Understanding how they formed not only sheds light on their own history, but also gives us insight into the broader history of the universe itself. Each galaxy holds a unique tale, shaped by the interplay of gravity, cosmic forces, and the fundamental particles that began as mere whispers within the fabric of space-time. The evolution of galaxies is a complex and captivating journey that spans billions of years, driven by multiple intertwined processes. At the heart of this cosmic transformation are gravitational forces. Galaxies form from vast clouds of gas and dust, which collapse under their own gravity. This initial clumping leads to the birth of stars, initiating a cycle that will shape the galaxy's characteristics for eons. As these stars burn out, they can explode in supernovae, scattering elements and material back into space, enriching the interstellar medium and nurturing future generations of stars. Another crucial aspect of galactic evolution is the merger of galaxies. Throughout cosmic history, galaxies are not passive structures. They collide and merge with one another. These galactic interactions can trigger bursts of star formation as gas clouds are compressed and heated during collisions. The gravitational interplay can also lead to a reorganization of star orbits within the merged galaxies, ultimately transforming their shapes and dynamics. Tidal forces during these encounters can even strip stars and gas from one galaxy and transfer them to another, reshaping their structures. Additionally, the influence of dark matter cannot be overlooked. This mysterious substance, which makes up a significant portion of the universe's mass, plays a vital role in the formation and stability of galaxies. Dark matter halos provide the gravitational foundation that helps galaxies gather more gas and form new stars. The mass of dark matter can affect the speed at which galaxies rotate, impacting their spiral structures and overall morphology. Over time, the dynamics of dark matter, in concert with visible matter, determine whether a galaxy will become a sprawling spiral, an elliptical, or another form entirely. Lastly, environmental factors such as the density of surrounding galaxies also drive evolution. In denser regions of space, known as galaxy clusters, interactions are more frequent, leading to phenomena like galaxy harassment. This term describes the gradual stripping of gas from galaxies in these crowded habitats, impacting star formation. In contrast, galaxies in more isolated regions can develop their own unique characteristics, influenced predominantly by internal processes. Through this lens, the life story of a galaxy is revealed to be a dynamic interplay between the gravitational dance of stars, mergers, dark matter, and their cosmic environment. Galactic collisions are among the most spectacular events in the cosmos, deeply influencing the structure of galaxies and ultimately the universe itself. When two galaxies interact, their gravitational pulls can create a dance of stars, gas, and dust that reshapes their very forms. These encounters can trigger new waves of star formation, as the dense clouds of gas are compressed and heated during the amalgamation. Over time, this can lead to the birth of millions of new stars, dramatically altering the galaxy's luminosity and character. What's more intriguing is the long-term outcome of these collisions. Often, galaxies do not simply merge and vanish. Instead, they can form new, larger entities known as elliptical galaxies. The Milky Way, our own home galaxy, is on a collision course with the Andromeda galaxy. When these two collide, in approximately 4 billion years, we can expect a transformation, one that will give rise to a new shape and stellar population. This merger will not only change the structure of our galaxy, but might also cause significant changes in the orbits of stars, leading to a repopulation of the galaxy's stellar inhabitants. Galactic collisions also influence the distribution of dark matter in the universe. Dark matter, which makes up about 27% of the universe and cannot be seen directly, interacts gravitationally with regular matter. As galaxies collide, the gravitational effects can alter the concentration and distribution of dark matter within and outside these galaxies. This interplay affects how galaxies cluster together, ultimately shaping the large-scale structure of the universe, where galaxies are found in groups and filaments separated by vast voids. Each galactic collision tells a story of creation and transformation. They have lasting effects that ripple through time and space, influencing everything from star formation to dark matter distribution. The universe is a dynamic tapestry knit together by these cosmic interactions, making it a fascinating subject for exploration and understanding. As we gaze into the depths of space, we can appreciate how these magnificent cosmic events help sculpt not only individual galaxies, but also the vast expanse of the universe we inhabit. Dark matter plays a pivotal role in the formation and evolution of galaxies. Although it cannot be seen directly, it constitutes about 27% of the universe's total mass and energy. This mysterious substance does not emit, absorb, or reflect light, making it invisible to traditional astronomical instruments. Yet, its influence is undeniable. Dark matter provides the gravitational scaffolding that allows galaxies to form and evolve, acting like an invisible glue that holds them together. When the universe was still in its infancy, shortly after the Big Bang, fluctuations in density created regions that were slightly more concentrated. These areas, filled with dark matter, acted as gravitational wells that pulled in regular matter. As this ordinary matter accumulated, it began to cool and collapse, eventually forming the galaxies we observe today. Without dark matter's gravitational pull, this clumping of matter would not have occurred efficiently, and galaxies might not have formed at all. As galaxies evolve, dark matter continues to play an essential role. It influences the rotation curves of galaxies. These are graphs showing how stars move at different distances from the galactic center. Traditional physics suggests that stars should orbit slower the further they are from the center, but observations show something different. The outer stars orbit at unexpectedly high speeds, indicating the presence of unseen mass, dark matter, surrounding the visible galaxy. Moreover, dark matter is crucial in the large-scale structure of the universe. It helps create a cosmic web, with galaxies and galaxy clusters forming along filaments of dark matter. These structures guide the motion and distribution of visible matter, shaping the universe as we know it. Through its gravitational interactions, dark matter is not just a passive player. It's an architect of the cosmos, molding galaxies and influencing their destinies across billions of years. Astronomers have developed a sophisticated toolkit to study galactic evolution, allowing them to peer back through time and uncover the story of how galaxies form and change. One of the primary methods involves observing light from distant galaxies. This light has traveled for billions of years, giving astronomers a snapshot of these galaxies at different stages of their life cycles. By measuring the redshift of this light, they can determine how fast a galaxy is moving away from us, which reveals important insights about the universe's expansion and the age of the galaxy itself. In addition to direct observations, astronomers utilize advanced computer simulations to model the processes that govern galactic formation and evolution. These simulations depend on complex physics to replicate conditions in the early universe, allowing scientists to visualize how galaxies might evolve over time. Through these models, researchers can investigate how factors such as gas dynamics, stellar formation, and dark matter influence the structural development of galaxies. Furthermore, astronomers examine the composition of stars within galaxies to understand their evolutionary stages. By analyzing the light from individual stars, they can determine their age, size, and chemical makeup. This information is crucial as stars are the building blocks of galaxies. The study of star populations helps astronomers piece together the history of mass accretion, merging events, and the subsequent cycling of matter that shapes the characteristics of galaxies. Finally, tools like powerful telescopes, including the Hubble Space Telescope and the more recent James Webb Space Telescope, play a crucial role. These instruments capture images and spectra from various wavelengths of light, providing a comprehensive view that spans the near-infrared to ultraviolet spectrum. With ongoing advancements in technology, astronomers continue to gain a deeper understanding of how galaxies evolve, revealing the intricate tapestry of cosmic history stretching back through vast distances and time. Spiral galaxies, including our own Milky Way, are characterized by their stunning pinwheel shape, which consists of a flat, rotating disk containing stars, gas, and dust. This disk features beautiful, sweeping arms that extend outward from the center. These arms are rich in young, hot stars that emit bright light, making them visually striking. The spiral structure is often contrasted with the more spheroidal, featureless shapes of elliptical galaxies. At the heart of spiral galaxies lies a dense concentration of older stars, along with a supermassive black hole. This central bulge is where the gravity is strongest, drawing in nearby stars and interstellar material. Its presence can affect the dynamics of the entire galaxy, influencing how stars orbit around the galaxy's center. Some studies suggest that such black holes can play a significant role in regulating star formation in the surrounding regions. The disk of a spiral galaxy is made up of a diverse mixture of ages among the stellar population. While some young, hot stars are luminous and vibrant, Older stars provide a contrasting backdrop of cooler, dimmer light. The interstellar medium within these galaxies is a crucial element, composed of gas and dust, which serves as the breeding ground for new stars. These regions of star formation often appear as bright nebulae, adding to the colorful tapestry of spirals. Another fascinating aspect of spiral galaxies is their rotation dynamics. The stars and gas in the outskirts of the galaxy rotate at similar speeds to those nearer the center, a phenomenon that cannot be fully explained by gravity alone. This discrepancy has led astronomers to propose the existence of dark matter, an invisible substance permeating the universe. Despite its elusive nature, dark matter is thought to significantly influence the structure and behavior of spiral galaxies, presenting one of the many mysteries that astronomers continue to explore. Elliptical galaxies present a fascinating contrast to other types of galaxies, particularly spirals and irregulars, in their evolution. One of the most striking characteristics of elliptical galaxies is their shape. They range from nearly spherical to more elongated forms, and they lack the defined structure found in spiral galaxies, which feature prominent arms and a well-defined disk. This absence of structure suggests a different evolutionary path, marked by less ongoing star formation and a more homogeneous composition. Throughout their lifetimes, elliptical galaxies predominantly grow through the merging of smaller galaxies. This process can lead to the formation of massive galaxies with vast quantities of stars, but it also disrupts the swirling patterns typical of star formation seen in spirals. Instead of continually forming new stars from dense gas clouds, ellipticals appear more evolved and are often populated by older, red stars. The merger events that contribute to their growth can strip away gas, reducing the material available for new star production and giving these galaxies their more subdued colors. Another aspect of their evolution is the role of supermassive black holes. Many elliptical galaxies host black holes at their centers that can be millions or even billions of times the mass of our Sun. The energy produced during galaxy mergers can fuel intense periods of activity, known as quasars, where gas and dust spiral into these black holes, emitting tremendous light. Over time, as the gas is depleted, the once vibrant activity subsides. This shift emphasizes the contrast between elliptical galaxies and their spiral counterparts, which can continue forming new stars due to their available gas reserves. Finally, the environment in which elliptical galaxies reside also influences their evolution. They are often found in dense clusters where gravitational interactions with neighboring galaxies can further accelerate their growth and shape their dynamics. As they interact, the structures within the galaxies change, leading to a more complex interplay of stellar populations and the eventual emergence of massive elliptical forms. The evolution of elliptical galaxies reflects their unique merging history, gas dynamics, and environmental influences, marking them as intriguing players in the cosmic narrative. Irregular galaxies are captivating celestial objects that draw the attention of astronomers for several compelling reasons. Unlike their more structured counterparts, such as spiral or elliptical galaxies, irregular galaxies defy the typical shapes and patterns we expect in the cosmos. Their chaotic forms can result from gravitational interactions with other galaxies or the remnants of smaller galaxies merging. This tumultuous nature makes them rich fields for study, offering insights into the processes that govern galaxy formation and evolution. One significant aspect of irregular galaxies is their high rate of star formation. These galaxies often contain abundant amounts of gas and dust, providing the essential ingredients for creating new stars. In some cases, they can produce stars at rates several times greater than that of the Milky Way. This vigorous activity allows astronomers to investigate not just how stars form, but also the conditions required for their birth. Understanding these processes plays a crucial role in piecing together the larger puzzle of cosmic evolution. Furthermore, irregular galaxies have been found to host a diverse range of celestial phenomena. They can exhibit unusual characteristics like massive star clusters, supernova remnants, and even active galactic nuclei. These features provide astronomers with opportunities to explore the fundamental truths of astrophysics. Studying these various phenomena helps scientists understand the life cycles of stars, the dynamics of gas clouds, and the complex interplay between star formation and galactic evolution. Finally, irregular galaxies can shed light on the early universe. Many of these galaxies are thought to be similar in structure to the galaxies that existed shortly after the Big Bang. By observing these galaxies today, astronomers gain a glimpse into the conditions of the universe when it was young. This makes irregular galaxies not only an exciting study of the present, but also a critical window into our cosmic past, enriching our understanding of where we come from in the grand tapestry of the universe. Starbursts are extraordinary events in the life of a galaxy, marked by a dramatic increase in the rate of star formation. This phenomenon occurs when gas and dust in a galaxy become compressed, often triggered by interactions with other galaxies or the collision of gas clouds. During a starburst, a galaxy can form thousands of new stars every year, far more than the typical rate for an average galaxy. This surge in stellar creation significantly impacts the galaxy's evolution over time. As these new stars ignite, they release vast amounts of energy and radiation. This influx of energy heats up the surrounding gas and triggers further star formation, creating a positive feedback loop that can last for millions of years. One fascinating aspect of starbursts is that they often produce massive, short-lived stars, which exert considerable influence on their surroundings. When these massive stars reach the end of their life cycles, they explode as supernovae, enriching the surrounding space with heavy elements. This process not only reshapes the galactic environment, but also contributes to the cosmic material available for later star formation. Moreover, starbursts can significantly alter a galaxy's morphological structure. Galaxies experiencing intense starburst activity may transform from spiral shapes into more irregular forms as star formation proceeds in chaotic bursts. This evolution can affect the galaxy's later characteristics, influencing its ability to host life-sustaining conditions. The energy released during a starburst can also drive powerful outflows of gas, redistributing material across the galaxy and affecting nearby galaxies' evolutionary narratives. Starbursts play a pivotal role in galactic evolution by increasing star formation, altering the physical structure of galaxies, and enriching the interstellar medium with heavy elements. These vibrant periods of activity not only contribute to the individual galaxy's life cycle, but also collectively shape the broader evolution of the universe, emphasizing the interconnectedness of galaxies across cosmic time. The cosmic web is the grand structure of the universe, a vast network that connects galaxies and clusters of galaxies. Imagine it as a sprawling tapestry woven from the threads of dark matter and gas that spans the entire cosmos. This web features a pattern of filaments that surround voids, creating an intricate framework in which most of the universe's visible matter is organized. This large-scale structure is crucial for understanding how galaxies form, evolve, and cluster, leading to the universe's current arrangement. The discovery of the cosmic web can be traced back to advancements in observational astronomy in the late 20th century. Researchers began to notice that galaxies weren't just scattered randomly throughout space. Instead, they appeared to follow specific patterns. The term cosmic web gained popularity in the 1990s, particularly with simulations that replicated the universe's large-scale structure based on the concepts of dark matter and cosmic inflation. One of the key breakthroughs in the understanding of the cosmic web came from the observation of the distribution of galaxies. Astronomers utilized large-scale surveys, including the 2-micron all-sky survey, to map the locations of galaxies across vast distances. These surveys revealed that galaxies avoid empty regions and cluster along thin strands, strongly supporting the idea of an interconnected web structure in the universe. Further insights from computational models and simulations illustrated how gravitational forces shaped these cosmic filaments over billions of years. These models showed that dark matter plays a pivotal role in guiding galaxies along the cosmic web, influencing their formation and interactions. The ongoing study of the cosmic web not only enhances our knowledge of cosmic evolution, but also deepens our understanding of the mysterious dark matter that permeates the universe. The cosmic web is a fascinating structure that shapes the universe on the grandest scales. It is a vast network of galaxies, galaxy clusters, and dark matter formed from the gravitational attraction between these massive elements. At its core, the cosmic web consists of filaments of galaxies and dark matter that stretch across the universe, interconnected like threads in an intricate tapestry. This network not only influences the distribution of galaxies, but also dictates how matter evolves across cosmic time. As we look deeper into the universe, we see that most of the galaxies are not evenly distributed. Instead, they are clustered along these filaments, often forming walls and sheets that create vast voids of empty space in between. These large-scale structures arise from the gravitational pull of dark matter, which acts like a scaffold for visible matter, guiding the formation and movement of galaxies. The interactions within this web also influence galaxy growth, as galaxies merge and form larger structures over billions of years. The dynamics of the cosmic web are largely governed by gravity, which plays a crucial role in shaping the universe's large-scale structure. As gas and dark matter fall into the potential wells created by these filaments, they compress and cool, eventually leading to star formation. This process creates new galaxies that further enhance the complexity of the cosmic web. Over time, these galaxies evolve, undergo cosmic interactions, and continue to repaint the large-scale structure of the universe. Understanding the cosmic web provides critical insights into the evolution of the universe. It helps astronomers interpret the distribution of galaxies, the properties of dark matter, and the overall dynamics of cosmic expansion. As research advances with increasingly sophisticated telescopes and simulations, our appreciation for this intricate cosmic network deepens, revealing the underlying order in the vastness of space and the profound interconnectedness of all cosmic structures. To explore the vast expanse of the universe, scientists employ a variety of techniques that enable them to observe and map the cosmic web, the intricate structure formed by galaxies and dark matter. One of the primary tools in their arsenal is the use of telescopes that operate across different wavelengths of light. Optical telescopes reveal galaxies and star clusters, while radio telescopes can detect hydrogen gas, which acts as a marker for areas of the universe rich in matter. By combining data from these different perspectives, astronomers can start to piece together a more complete picture of the cosmic web. One innovative method involves the use of large survey projects that systematically scan the sky. These projects, such as the Sloan Digital Sky Survey, gather immense amounts of data regarding the distribution and movement of galaxies. By cataloging billions of celestial objects, scientists can create a three-dimensional map of the universe, revealing how galaxies are interconnected and distributed in clusters and filaments. This massive effort not only sheds light on the structure of the cosmic web, but also enhances our understanding of cosmic evolution over billions of years. In addition to survey data, scientists utilize computer simulations to model the formation and growth of the cosmic web. These simulations take into account the laws of physics alongside observations gathered from the universe. By mimicking the conditions of space, they can predict how matter clusters under the influence of gravity, providing a valuable framework against which observational data can be compared. This back and forth between observation and simulation helps refine our knowledge of dark matter, which remains one of the cosmos's biggest mysteries. Another vital technique is the analysis of gravitational lensing. This phenomenon occurs when massive objects, such as galaxy clusters, warp the fabric of space-time, bending the light from objects beyond them. By studying how light is distorted on its journey to Earth, scientists can infer the presence and distribution of dark matter, as well as map the structure of the cosmic web. Together, these various techniques enable researchers to construct a detailed and dynamic representation of the universe's grand architecture, helping us unravel the mysteries of cosmic evolution and the fundamental forces governing it. The cosmos is not just a vast expanse of empty space, it is intricately woven into a colossal structure known as the cosmic web. This captivating arrangement resembles a cosmic tapestry, with filaments and voids forming its foundational elements. Filaments are massive strands of galaxies and dark matter that stretch across the universe, while voids are the nearly empty spaces between these filaments. Together, they compose the large-scale structure of the universe, demonstrating how matter is organized on the grandest scale. The formation of this complex structure begins with the Big Bang, when matter was distributed unevenly in the early universe. Over billions of years, small fluctuations in density caused the material to begin clumping together due to gravitational attraction. These clumps gradually evolved into galaxies, while the regions with less matter expanded into vast voids. As gravity continued to pull matter together, these filaments grew denser, connecting clusters of galaxies and forming a network that resembles a web. Interestingly, the balance between filaments and voids is crucial in shaping the universe's dynamics. The filaments create paths through which galaxies can move, while the voids provide areas of low density that allow for the expansion of space. This intricate dance of matter influences the distribution of galaxies we observe today. By mapping these structures, scientists have been able to confirm the existence of dark matter, hypothesized to be the unseen glue holding this grand design together. What's truly fascinating is how the cosmic web intimately relates to our understanding of the universe's history and future. The gravitational interactions within these structures not only guide galaxy formation, but also serve as indicators of the universe's fate. As the universe continues to expand, the intricate balance of filaments and voids will play a pivotal role in determining the ultimate destiny of galaxies and the very fabric of the cosmos itself. Dark matter is a cornerstone of our understanding of the universe's structure. It does not emit, absorb, or reflect light, making it invisible to our telescopes. Yet, it makes up about 27% of the universe, profoundly influencing its formation and evolution. A crucial aspect of dark matter is its gravitational pull, which acts as an unseen adhesive that holds galaxies and galaxy clusters together as they form. In the early universe, shortly after the Big Bang, matter existed in a nearly uniform distribution. However, tiny fluctuations in density allowed regions with slightly more mass to attract surrounding matter. As regular matter began to clump together due to gravity, dark matter served as the scaffolding around which galaxies and galaxy clusters could develop. This process led to the creation of vast structures we refer to as the cosmic web, composed of thin filaments of galaxies and vast voids between them. The cosmic web can be visualized as a delicate lacework, with dark matter forming the thick threads that connect galaxies. As normal matter gathers within these dark matter halos, it eventually cools and collapses, forming stars and galaxies. Thus, dark matter acts like a gravitational glue, facilitating the accumulation of visible matter and enabling the birth of cosmic structures. This dynamic relationship between dark matter and visible matter has been crucial for shaping the universe as we know it today. Understanding dark matter's role not only sheds light on the formation of galaxies, but also uncovers the fundamental processes that govern the large-scale structure of the cosmos. It continues to be a focal point of research in astrophysics, along with the ongoing quest to fully understand the mysterious nature of dark matter itself. Galaxy clusters are fascinating structures in the universe, acting as significant nodes within the cosmic web. This cosmic web is the vast interconnected framework of galaxies, gas, and dark matter that shapes the large-scale structure of the universe. These clusters are formed through the gravitational attraction of matter, accumulating both galaxies and dark matter over time. Each galaxy cluster serves as a gathering point for numerous individual galaxies, often grouped tightly together. Some of these clusters can host thousands of galaxies, highlighting their importance as hubs of formation and evolution within the universe. Surrounding these clusters is a filamentary structure made up of dark matter and gas. connecting them to other clusters and forming an intricate network that resembles a giant spider web across the cosmos. The distribution of galaxy clusters reveals much about the gravitational forces at play in the universe. Even the locations of these clusters can hint at the underlying dark matter distribution, as areas with a higher concentration of matter lead to more clusters forming. This means that by studying galaxy clusters, astronomers can gain insights into the large-scale structure of the universe, as well as the fundamental nature of dark matter itself. Moreover, galaxy clusters are sites of immense physical phenomena. They often contain hot gas that emits X-rays, and the gravitational interactions between galaxies can lead to dynamic processes such as galaxy mergers. This makes them not only key components of the cosmic web, but also important laboratories for understanding cosmology, the evolution of galaxies, and the nature of the universe at large. The cosmic web is a massive, intricate structure that resembles a vast network of filaments made from dark matter, gas, and galaxies stretching across the universe. It acts as a guiding framework for the distribution of galaxies, influencing where they cluster and how they interact. This web-like arrangement is formed by the gravitational pull of dark matter, which shapes the distribution of visible matter. The galaxies do not just scatter randomly through space, rather, they align along these filaments, which are the densest regions of matter in the universe. Within the cosmic web, we find three primary components: filaments, nodes, and voids. The filaments are long, thread-like structures where galaxies are densely packed. The nodes are the intersections of these filaments, acting as hubs of galaxy clusters. In contrast, the voids are vast empty spaces where few galaxies exist. The gravitational forces at play within this web encourage galaxies to move along these filaments, leading to the formation of clusters that can contain hundreds or even thousands of galaxies. Moreover, the cosmic web affects galaxy formation and evolution. Areas where filaments converge generate significant gravitational forces, which can trigger the collapse of gas clouds to form new stars and galaxies. As galaxies interact and merge within these clusters, they can influence one another, leading to phenomena such as galaxy collisions or the stripping of gas, impacting their future development. The cosmic web is a fundamental architect in the grand design of the universe, dictating not just where galaxies are located, but also how they evolve over billions of years. The impact of the cosmic web extends beyond mere distribution. It has profound implications for our understanding of cosmic evolution. As we explore these structures, astronomers gather valuable insights into the history of the universe, the nature of dark matter, and the processes that govern galaxy formation. The cosmic web serves as a reminder that the universe is a dynamic and interconnected system where every galaxy plays a role in a much larger cosmic tapestry. The Big Bang is the prevailing cosmological model that explains the origin and evolution of our universe. It suggests that around 13.8 billion years ago, the universe began as an extremely hot and dense point, which rapidly expanded. This expansion set into motion the formation of all matter, energy, space, and time that we observe today. From this initial explosive event, the universe has continued to expand, cooling down over time, allowing for the formation of galaxies, stars, and planets. Support for the Big Bang theory comes from several key pieces of evidence. One of the most significant is the discovery of cosmic microwave background radiation. This faint glow, which fills the universe, is a remnant heat signature from the early universe, now cooled and stretched over billions of years. It serves as a snapshot of the universe when it was merely a hot plasma, and its uniformity across the sky reinforces the idea that the universe began in a hot, dense state. Another compelling piece of evidence is the observation of the redshift of distant galaxies. As light travels from an object moving away from us, it shifts towards the red end of the spectrum. This phenomenon shows that galaxies are moving away, indicating that the universe is still expanding. The farther a galaxy is from us, the faster it appears to be receding. This observable trend aligns perfectly with predictions made by the Big Bang model, suggesting that the universe has been expanding since its inception. Finally, the abundance of light elements, such as hydrogen, helium, and lithium, observed in the universe also supports the Big Bang theory. Predictions made by this model indicate that these elements should have been formed in significant quantities during the first few minutes after the Big Bang. Measurements of the actual amounts of these elements in the cosmos closely match those predictions, lending further credence to the theory. Collectively, these pieces of evidence weave a compelling narrative that enhances our understanding of the universe's beginnings and its ongoing transformation. The Big Bang theory provides a compelling explanation for the elemental composition of the universe, particularly the abundance of light elements such as hydrogen, helium, and lithium. According to this theory, the universe began as an incredibly hot, dense point around 13.8 billion years ago. As it rapidly expanded, it cooled down, allowing for the formation of fundamental particles and eventually simple atomic nuclei. In this early phase, which is referred to as nucleosynthesis, the conditions were just right for the production of light elements. After about 3 minutes, temperatures had dropped enough for protons and neutrons to combine and form the nuclei of hydrogen and helium, with some lithium also produced. Researchers estimate that roughly 73% of the matter produced in the universe at this stage was hydrogen, while about 25% was helium, and the remaining 2% was made up of traces of lithium and other light elements. The existence of these elements in such quantities has been confirmed through observational data. For example, we can see the spectra of distant stars and galaxies, which reveal a consistent prevalence of hydrogen and helium, matching predictions from the Big Bang model. This abundance of light elements, along with their relative proportions, serves as a cornerstone of evidence supporting the Big Bang theory. In contrast, heavier elements like carbon, oxygen, and iron were not produced in significant amounts during the Big Bang. Instead, they emerged later, formed through a variety of processes in the interiors of stars and during explosive events such as supernovae. Thus, the Big Bang theory not only accounts for the initial abundance of the light elements, but also sets the stage for the stellar processes that create heavier elements, illustrating the dynamic evolution of the cosmos. The earliest moments of the universe, often referred to as the Big Bang, remain enshrouded in profound mysteries. In the first few moments after the universe began, it expanded and cooled rapidly in a process known as cosmic inflation. This inflationary period raised numerous questions, particularly about what triggered this dramatic expansion and how it shaped the cosmos we observe today. The exact mechanisms behind inflation are still not fully understood, leaving scientists to piece together how this rapid growth occurred and what forces were at play in that primordial chaos. Another captivating mystery involves the nature of dark matter and dark energy, which together constitute a significant portion of the universe's mass-energy content. Observations suggest that around 27% of the universe is made up of dark matter, while about 70% is dark energy, yet their exact identities remain elusive. In the infant universe, conditions were so extreme that these exotic forms of matter and energy could have influenced structure formation. Understanding how dark matter interacted during these formative moments may uncover answers to why galaxies formed in the manner observed today. Additionally, the concept of the singularity at the very beginning of time raises challenging questions. Singularities, where density and gravity become infinite, challenge our understanding of physics as we know it. Both quantum mechanics and general relativity struggle to describe what happened at that moment, leaving an intellectual gap in our comprehension of cosmic beginnings. Some physicists propose that a theory of quantum gravity could help bridge this divide, offering insights into the very nature of space and time before the Big Bang. Finally, the echoes of the early universe are embedded in the cosmic microwave background radiation, which serves as a remnant from that heated state. While we have mapped this radiation extensively, anomalies and fluctuations within it hint at processes we have yet to fully grasp. These fluctuations may provide clues about how matter clumped together, leading to the formations of stars and galaxies. As technology advances, we continue to explore these lingering mysteries, and each discovery offers a tantalizing glimpse into the universe's first moments, revealing complexities that deepen our fascination with the cosmos. Cosmic inflation has significantly refined our understanding of the Big Bang model, providing a more comprehensive framework to explain the universe's early moments. Initially, the Big Bang theory described the universe as expanding from an extremely hot and dense state. However, it faced challenges, particularly when trying to explain the uniformity of the cosmic microwave background radiation and the large-scale structure of the universe. This is where inflation comes in. Inflation proposes that in the first moments after the Big Bang, the universe underwent an incredibly rapid expansion, expanding faster than the speed of light. This expansion stretched out space itself, smoothing out any irregularities and explaining why regions of the universe that are far apart still have the same temperature today. By introducing this short, explosive growth phase, inflation provides answers to some of the lingering questions about how the universe became so uniform and isotropic. Moreover, inflation offers a mechanism for the formation of galaxies and large-scale structures. Tiny fluctuations in energy density during the inflationary period were stretched across the cosmos, seeding the variations we observe in the distribution of galaxies today. These variations provide the gravitational pull required for clumping matter together, ultimately leading to the rich tapestry of galaxies and clusters we see across the universe. Cosmic inflation not only enhances the Big Bang model by addressing its shortcomings, but also connects the universe's beginnings to its current structure. This relationship between early growth and current observations deepens our understanding of cosmic evolution, highlighting the intricate dance of forces that has shaped the universe over billions of years. The Big Bang theory stands as the prevailing explanation for the origins of our universe. However, alternative cosmologies have emerged that challenge its tenets. One of the notable alternatives is the steady-state theory, which posits that the universe is eternal and always expanding while simultaneously creating new matter. Proponents of this theory argue that this scenario elegantly explains the universe's uniformity without requiring a singular moment of creation. Another challenge comes from the idea of cyclic models. These propose that the universe undergoes endless cycles of expansion and contraction rather than originating from a singular Big Bang event. Such models suggest that the universe could go through phases of evolution infinitely, which raises compelling questions about time and the nature of the cosmos. Then there's the concept of the multiverse. This theory suggests that our universe is just one of many, possibly with different physical laws and constants. Advocates of the multiverse contend that elements of our universe, which seem peculiar under the Big Bang theory, can be better understood when considering a greater framework of multiple universes. This challenges the notion that our cosmos holds unique significance. Finally, the emergence of quantum gravity theories introduces an additional layer of complexity. These theories attempt to merge quantum mechanics with general relativity, hinting at behaviors of spacetime that diverge from classical Big Bang predictions. While these alternative models provide fascinating insights, they also highlight the ongoing quest in cosmology to understand the universe better and refine or expand our existing theories. Current observations critically test and challenge the Big Bang paradigm through various methods, examining the universe's structure, composition, and evolution. For instance, astronomers utilize advanced telescopes to study the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation provides a snapshot of the universe during its infancy, revealing fluctuations in temperature that inform scientists about the distribution of matter and energy. These observations have largely supported the Big Bang model, but also raise critical questions about the conditions that led to its initial expansion. Another area of scrutiny comes from the study of galaxy formation and distribution. Observations of distant galaxies reveal an unexpected level of structure in the universe, suggesting that galaxies formed earlier than the Big Bang theory initially predicted. This phenomenon challenges models that rely on slow and gradual formation processes and instigates further investigation into alternative theories such as the possibility of a phase of rapid cosmic inflation. These factors compel scientists to reconcile discrepancies between theoretical predictions and empirical data. Dark matter and dark energy also play crucial roles in these discussions. The Big Bang theory encompasses the existence of dark matter to account for the gravitational effects observed in galaxy clusters. However, the true nature of dark matter remains elusive, prompting questions about whether our understanding of cosmology requires an overhaul. Similarly, dark energy, which drives the accelerated expansion of the universe, introduces further complexities. As scientists work to refine models of these mysterious components, they continually assess their implications for the Big Bang paradigm. In each of these areas, evolving observations serve as both a backbone for validating the Big Bang theory and a catalyst for potential revisions. As our scientific tools and measurements become increasingly sophisticated, the intricate tapestry of the universe continues to reveal new layers of complexity. Ultimately, this dynamic interplay between observation and theory fuels our understanding of the cosmos, ensuring that our journey to comprehend its origins is far from over. Primordial fluctuations are small, random variations in density that emerged in the early universe shortly after the Big Bang. These fluctuations are the seeds from which all cosmic structures, galaxies, stars, and clusters eventually formed. Imagine the universe as a vast ocean, where these tiny ripples set the stage for the formation of islands and continents over time. Without these fluctuations, the universe would likely have remained a homogeneous sea of particles, lacking the richness and diversity of structures that we observe today. The process began during the inflationary period, a fraction of a second after the Big Bang, when the universe expanded exponentially. During this rapid expansion, quantum fluctuations were stretched to macroscopic scales. These density variations influenced how matter clumped together under the force of gravity. Regions of slightly higher density attracted more matter, while less dense regions became voids. Over billions of years, these early fluctuations evolved, sculpting the fabric of the cosmos. As galaxies began to form and the universe continued to expand, these primordial fluctuations left an imprint that we can still observe today. The cosmic microwave background radiation, a remnant of the Big Bang, provides a snapshot of the universe when it was just about 380,000 years old. This background radiation reveals patterns that correspond to those early density fluctuations, giving us a glimpse into the conditions that led to the large-scale structure we see now. Astrophysicists have meticulously studied these fluctuations to understand the universe's evolution. By examining their distribution and characteristics, they uncover clues about fundamental forces and the ingredients that shaped our cosmic environment. Primordial fluctuations are more than just remnants of the Big Bang. They are the fundamental building blocks of cosmic structure, providing insight into the universe's trajectory from its fiery beginnings to the complex tapestry of galaxies and clusters we observe today. Quantum mechanics and general relativity are two foundational pillars of modern physics, yet they exhibit a profound tension when it comes to understanding the universe. Quantum mechanics focuses on the behavior of the very small, governing the world of subatomic particles and their strange probabilistic nature. In contrast, general relativity describes the cosmos on a grand scale, explaining how massive objects like stars and galaxies warp the fabric of spacetime, creating what we perceive as gravity. While each theory works beautifully in its domain, merging them into a cohesive framework presents significant challenges. One of the primary areas of conflict arises when trying to apply quantum mechanics to cosmological phenomena, such as black holes. According to general relativity, a black hole's core collapses into a singular point where density becomes infinite, and the laws of physics as we know them cease to operate. However, quantum mechanics suggests that information cannot be entirely lost, an idea that conflicts with the notion of an impenetrable singularity. This disagreement leads to paradoxes like the famous black hole information paradox, which continues to puzzle scientists, urging them to rethink the principles of reality. Another point of contention is the fate of the universe itself, particularly in the context of the Big Bang. General relativity predicts an expanding universe originating from a singular point, while quantum mechanics introduces a level of unpredictability into the early universe's conditions. Concepts like quantum fluctuations may have played a crucial role in the rapid expansion known as inflation, suggesting that quantum effects could have influenced the very structure of the cosmos. Yet the exact manner in which these two frameworks interact in that highly energetic environment is still a mystery. Efforts to bridge the gap between quantum mechanics and general relativity are ongoing as physicists explore theories like quantum gravity and string theory. These innovative approaches aim to create a unified picture of the universe that encompasses both the minuscule and the colossal. The quest for a reconciliation of these two theories not only intrigues scientists but also holds the potential to unlock deeper insights into the nature of reality itself, pushing the boundaries of human understanding in cosmology. The quantum vacuum is a fascinating concept at the intersection of quantum mechanics and cosmology. Contrary to our everyday understanding of a vacuum as an empty space devoid of matter, the quantum vacuum is a seething field filled with dynamic activity. This vacuum is not truly empty. Rather, it is teeming with virtual particles that pop in and out of existence in a constant dance dictated by the principles of quantum theory. These fleeting particles can affect physical phenomena in ways that are both surprising and profound. In the context of cosmic evolution, the quantum vacuum plays a pivotal role. Some theories suggest that fluctuations in the quantum vacuum could provide the seeds for cosmic structures, influencing the formation of galaxies and clusters. The energy associated with these vacuum fluctuations can create tiny differences in pressure, which might be crucial in the gravitational processes leading to the formation of larger cosmic entities. Therefore, the quantum vacuum acts like a cosmic backdrop, continuously contributing to the evolution of the universe. Moreover, the idea of a dynamic vacuum has implications for the very fabric of space and time. Researchers speculate that the energy present in the quantum vacuum could drive the accelerated expansion of the universe, a phenomenon observed in recent cosmological studies. This acceleration suggests that an unseen force, commonly labeled dark energy, may be linked to the energy density of the quantum vacuum. This connection provokes profound questions about the nature of the universe, challenging our understanding of gravity and the fundamental forces at play. As scientists delve deeper into the mysteries of the quantum vacuum, our grasp of cosmic evolution continues to expand. Investigations into these quantum properties not only enhance our understanding of the cosmos, but also inspire new philosophical inquiries about existence itself. With each discovery, we edge closer to understanding how this invisible framework impacts the grand tapestry of the universe and our place within it. Studying quantum phenomena at astronomical scales is a fascinating intersection of two seemingly disparate fields: quantum mechanics and cosmology. While quantum mechanics operates on the scale of subatomic particles, cosmology often focuses on the vast universe encompassing galaxies and dark matter. To bridge this gap, scientists employ a variety of innovative techniques and technologies. One key method involves using advanced telescopes and observational instruments that can detect ultra-precise signals from cosmic sources. For example, scientists look for the faint echoes of gravitational waves, ripples in space-time that provide insights into events like black hole mergers. These gravitational waves are influenced by quantum effects at their origins, giving researchers clues about how quantum mechanics operates within the larger universe. As such, they offer a window into phenomena that transcend ordinary scales, revealing how the microscopic influences the macroscopic. Additionally, experiments like those conducted at the Large Hadron Collider demonstrate how scientists can recreate conditions similar to those in the early universe. By smashing particles together at incredibly high energies, researchers probe the fundamental building blocks of matter and the forces that govern them. These experiments can yield results that help understand the quantum processes that may have occurred during cosmic events such as the Big Bang. Moreover, the development of quantum technologies, like quantum computing and quantum sensors, is opening new avenues for exploring the cosmos. These technologies enhance our ability to simulate quantum systems and measure tiny fluctuations in cosmic signals. As researchers continue to push the boundaries of our understanding, they gradually unveil the mysteries that lie at the intersection of the quantum realm and the grand scale of the universe. The endeavor is an exciting testament to human curiosity and the relentless pursuit of knowledge. Virtual particles are a fascinating aspect of quantum field theory that intrigue scientists and laypersons alike. While they might not be seen or directly detected, these fleeting entities can offer profound insights into the cosmos. Essentially, virtual particles are temporary fluctuations in energy that arise even in seemingly empty space. They pop in and out of existence so rapidly that they remain undetectable by standard means. Yet, their effects can be witnessed in various cosmic phenomena. One key area where virtual particles make their presence known is in the phenomenon known as Hawking radiation. Named after the renowned physicist Stephen Hawking, this theoretical prediction suggests that black holes can emit radiation caused by pairs of virtual particles forming just outside their event horizons. In this extreme environment, one particle can fall into the black hole while the other escapes, lending credence to the idea that black holes can lose mass over time, ultimately leading to their evaporation. This concept challenges our understanding of physics, showing that black holes are not entirely black after all. Virtual particles also play a significant role in the concept of vacuum energy. The vacuum of space is not just empty, but rather a bubbling sea of energy filled with virtual particles constantly interacting. This energy can influence the fabric of space-time itself, connecting to the idea of dark energy, which is believed to be driving the accelerated expansion of the universe. The relationship between vacuum energy and dark energy remains a subject of vigorous research, pushing the boundaries of our understanding of the universe. Moreover, the implications of virtual particles extend to the study of forces between particles, such as electromagnetism and the strong force. Virtual particles act as messengers in these fundamental forces, facilitating interactions even at a distance. This corner of quantum mechanics not only underpins high-energy physics experiments, but also provides a crucial framework for understanding the interconnectedness of the universe. As scientists continue to explore the mysterious world of virtual particles, insights gained may unlock further secrets of the cosmos, bridging the gap between the very small and the very large. Quantum entanglement is one of the most fascinating phenomena in the realm of quantum mechanics. It describes a connection between particles that allows them to be linked together, regardless of the distance separating them. When two particles become entangled, the state of one particle can instantaneously affect the state of the other, even if they are light years apart. This seemingly paradoxical relationship challenges our traditional notions of space and time, offering tantalizing hints about the very fabric of the universe. Scientists are increasingly looking at entanglement as a potential key to unlocking the mysteries of the cosmos. One area where entanglement could prove invaluable is in understanding the connections between fundamental forces such as gravity and electromagnetism. By exploring how entangled particles behave under extreme conditions, like those found near black holes or during the Big Bang, researchers hope to gather insights into the underlying structure of space-time itself. Furthermore, quantum entanglement offers possibilities in the field of quantum information science. It has the potential to revolutionize our approach to computing and communication, with concepts like quantum teleportation and quantum cryptography emerging from this phenomenon. As we develop technologies that harness entanglement, we could not only unlock practical applications, but also deepen our understanding of the universe's intricate workings. Quantum entanglement is not just a perplexing curiosity of physics, it serves as a bridge toward comprehending the deeper laws governing our universe. As scientists continue to probe its mysteries, we may find ourselves one step closer to unraveling the secrets of existence itself, revealing the interconnectedness of all things in ways we have yet to fully grasp. The exploration of theoretical quantum black holes opens up exciting possibilities for understanding the fundamental nature of gravity and the universe itself. At its core, a black hole represents a region in space where gravity is so strong that nothing, not even light, can escape. Traditional physics, governed by general relativity, describes the behavior of these massive objects, but it does not account for quantum mechanics, which rules the very small scales of atoms and subatomic particles. Quantum black holes, hypothesized in various theories, particularly in the context of string theory and loop quantum gravity, challenge our conventional views. They suggest that black holes could be more than just singularities, points in space with infinite density, but rather entities that might preserve information about the matter that falls into them. This idea resonates with the concept of information preservation in quantum mechanics, leading to what is often referred to as the information paradox. By studying these quantum aspects, scientists hope to resolve this paradox and deepen our comprehension of how information is conserved in the universe. Moreover, theoretical quantum black holes have the potential to bridge the gap between the forces of gravity and the principles of quantum mechanics. In doing so, they can provide insights into the unification of forces, a long-sought goal in physics that would allow scientists to describe all fundamental interactions under one framework. This unification could lead to a new understanding of space and time, suggesting they might not be the smooth continuum we perceive, but rather composed of discrete units at the quantum level. While still speculative, the exploration of quantum black holes invites researchers to re-examine established theories, pushing the boundaries of our knowledge. Each step towards understanding these exotic objects not only deepens our grasp of gravity, but also enriches our views on the cosmos. In the ongoing quest to understand the universe, theoretical quantum black holes stand at a fascinating crossroads of science, where the realms of the very large and the very small intersect. The concept of the multiverse proposes that our universe might be just one of many, possibly infinite, universes existing simultaneously. This intriguing idea arises from several leading theories in physics and cosmology, each providing unique perspectives on how multiple universes could arise. One significant theory is based on inflation, a rapid expansion that the universe underwent shortly after the Big Bang. During this inflationary phase, tiny quantum fluctuations could lead to regions of space that expand differently, resulting in distinct universes with varying physical laws and constants. Some scientists suggest that these pocket or bubble universes can form in an ever-expanding multiverse, each occupying its own space, yet emerging from the same overall inflationary event. Another theory supporting the multiverse idea comes from string theory. This complex framework attempts to reconcile quantum mechanics and general relativity by proposing that fundamental particles are not point-like, but rather tiny, vibrating strings. In string theory, the fabric of spacetime includes additional dimensions beyond the familiar three. The way these dimensions are curved or compactified could lead to a multitude of distinct universes, each with its own set of physical rules shaped by different configurations of these additional dimensions. Finally, the many-worlds interpretation of quantum mechanics offers a fascinating perspective on the nature of reality. According to this interpretation, every event that has multiple possible outcomes leads to the branching of the universe into countless versions, each realizing one of the possible outcomes. Thus, every choice or decision creates a new universe where different possibilities unfold. Collectively, these theories present a compelling narrative for the existence of a multiverse, captivating both scientists and enthusiasts alike as they explore the profound implications of what lies beyond our own universe. The concept of parallel universes, often referred to as the multiverse theory, opens up fascinating avenues for understanding reality. At its core, this idea posits that our universe is just one of many. Each of these universes could possess different physical laws, constants, and even histories. This intriguing hypothesis challenges our traditional view by suggesting that there could be countless variations of reality, each unfolding in its own unique way. One of the most compelling aspects of parallel universe theories is their impact on fundamental questions about existence. For instance, consider the implications for life and consciousness. If there are multiple universes, it raises the possibility that alternative versions of ourselves exist in other realms, making decisions differently or leading entirely different lives. This notion shifts our perspective on individuality and fate, prompting us to ponder how many paths our lives could take under different circumstances. Additionally, the multiverse concept finds grounding in various scientific theories, particularly in quantum physics and cosmology. The infamous many worlds interpretation of quantum mechanics suggests that every time a decision is made, the universe branches into separate timelines, each representing a different outcome. This concept provides a rich framework for exploring the probabilistic nature of reality and offers a scientific basis for the existence of countless alternate universes. Finally, the parallel universe theory encourages a broader inquiry into the nature of existence itself. As we probe deeper into the cosmos, we might discover that our understanding of reality must be far more expansive than we ever imagined. By contemplating the possibility of parallel universes, we not only confront the limits of our knowledge, but also ignite our curiosity about the vast, uncharted territories of existence that await exploration. The multiverse hypothesis suggests that our universe is just one of many, potentially countless, universes coexisting within a vast cosmos. This idea challenges our traditional understanding of the universe and raises profound questions about existence. Although the multiverse may sound like science fiction, there are several theoretical frameworks and observations that could lend support to this intriguing concept. One of the key pieces of evidence comes from cosmic inflation, a theory that describes how the universe expanded rapidly just after the Big Bang. Some versions of this theory propose that inflation did not occur uniformly, meaning that while our observable universe went through this rapid expansion, other regions of space did not, leading to the creation of pocket or bubble universes. If inflation can create these separate regions, it implies the existence of other universes beyond our own, each with different physical laws or constants. Another intriguing hint comes from the concept of quantum mechanics. The many worlds interpretation suggests that all possible outcomes of a quantum event actually occur in their own distinct universes. This line of thinking proposes an infinite number of branch points where each decision creates a split in reality. While this remains a philosophical discussion as much as a scientific one, it opens the door to considering our universe as part of a much larger multiverse framework. Finally, there are observational hints, albeit indirect, that could support the multiverse hypothesis. For instance, researchers have detected anomalies in the cosmic microwave background radiation, the afterglow of the Big Bang. Some interpret these anomalies as evidence that our universe may have collided with another universe, which could imply the existence of other realms. While compelling, these ideas remain speculative and require more rigorous testing. As science progresses, the mysteries of the multiverse continue to excite and challenge our understanding of reality itself. String theories propose a fascinating framework for understanding the fabric of the universe. At its core, string theory suggests that the fundamental particles we know, like electrons and quarks, are not point-like entities, but instead are tiny, vibrating strings. These strings can vibrate at different frequencies, and the mode of vibration determines the type of particle formed. This simple premise carries profound implications, particularly when we examine our universe and the intriguing notion of multiple or parallel universes. One of the compelling aspects of string theory is its inherent flexibility when it comes to dimensions. While we typically experience a universe with 3 spatial dimensions, string theory posits the existence of additional, compact dimensions that are not readily observable. These extra dimensions can influence the properties of particles, leading to variations in physical laws. This could allow for entire universes with different characteristics, potentially resulting in a vast multiverse where each universe operates under its own unique set of rules. Moreover, there are multiple versions of string theory, each with distinct implications for the universe. Some branches suggest that our universe could be one among countless others, each created during different phases of the string universe's evolution. These ideas stem from the concept of brains, which are multidimensional objects within string theory. Universes may exist as separate brains within a higher dimensional space, occasionally interacting or colliding, generating new universes in what could be a cosmic web of parallel realities. The multiverse theory arising from string theory not only challenges our understanding of reality, but also ignites imagination about the nature of existence. If multiple universes do coexist, it raises profound questions about the laws of physics and our place within this cosmic tableau. Are we mere observers in a vast landscape filled with alternate realities? The intersection of string theory and the multiverse idea pushes the boundaries of science, inviting both questions and exploration into the depths of existence itself. This ongoing inquiry reflects the enduring human curiosity about the universe and our quest for understanding within its limitless possibilities. The concept of a multiverse suggests that our universe is just one of many existing within a vast and possibly infinite collection of universes. This idea fundamentally reshapes our understanding of time, challenging the linear perspective we have grown accustomed to. If multiple universes exist, each could have its own distinct properties governing time. Some might experience time as we do, while others could have entirely different temporal mechanics. One fascinating implication of a multiverse is that time might not be universally constant. In our universe, time is woven into the fabric of space, forming what we know as space-time. However, in alternate universes, time could behave differently under varying physical laws or conditions. For instance, in a universe with a different speed of light or varying forces, the flow and experience of time might diverge significantly from our own. Additionally, the multiverse theory prompts questions about the nature of time itself. Is time a fundamental aspect of reality, or is it an emergent phenomenon influenced by the interactions of particles and forces? In a multiverse where different dimensions and physical laws exist, time could reveal itself as a flexible and malleable entity, allowing for new perspectives on causality and the sequence of events. Moreover, each universe might represent different historical timelines or outcomes. Imagine a scenario where decisions made at key moments in our lives create branches into different realities. In this case, time does not flow linearly, but becomes a collection of divergent paths. This opens the door to exciting philosophical discussions on fate, free will, and how we perceive our own existence within this complex tapestry of universes. The exploration of time in a multiverse scenario not only challenges our understanding of the cosmos, but also invites us to reflect on our place within it. The notion of a multiverse, where countless universes coexist with varying physical constants and laws, emerges as a fascinating extension of cosmic inflation theory. Cosmic inflation describes a rapid expansion of the universe during its earliest moments, a period that set the stage for the cosmos as we know it. This theory posits that inflation not only smoothed out the universe, but also gave rise to significant fluctuations in energy densities, which eventually led to the formation of galaxies and large-scale structures. As researchers delve deeper into the implications of cosmic inflation, they find that it can lead to a multiverse scenario. In this view, the rapid expansion could produce pocket or bubble universes, each with different physical properties. These bubbles can sprout from a common inflating field and grow independently, resulting in a vast collection of universes, each with their own unique characteristics. One implication of this is that the conditions we observe in our universe might just be one possibility among countless others, shaped by random fluctuations in the inflating field. Additionally, the concept of cosmic inflation challenges our understanding of what is truly possible. If our universe is just one bubble in this vast multiverse, then the diversity of cosmic laws could redefine fundamental questions about existence, life, and the parameters that govern everything from the forces of nature to the very particles that make up matter. This perspective shifts scientific inquiry from merely understanding our universe to also considering how different conditions could lead to entirely different realities. Ultimately, the multiverse not only expands the canvas on which cosmologists paint their theories, but also invites us to reconsider the nature of reality itself. The intersection of cosmic inflation and multiverse theory encourages an open exploration of what lies beyond our immediate existence, hinting at the vast, complex tapestry that constitutes the cosmos. Each discovery in this fascinating area continues to push the boundaries of our understanding, promising to unravel more about the nature of reality, time, and space. Multiverse theories evoke a fascinating array of philosophical questions that probe the very nature of reality and existence. At the forefront is the question of what it means for something to exist. If multiple universes are constantly branching out from one another, how do we define our own reality amidst countless others? This notion prompts reflection on the nature of identity and the criteria that grant worth to our experiences in a singular universe compared to the infinite possibilities laid out by the multiverse concept. Another intriguing philosophical implication involves determinism and free will. In a multiverse, if every possible outcome exists in a different universe, do our choices matter? This challenges the very foundation of personal agency, suggesting that our actions lead to countless alternate realities where different decisions have been made. Such a perspective could lead to existential contemplations about fate versus free will, and whether our sense of agency is an illusion in a reality where every possibility plays out somewhere. Additionally, multiverse theories raise questions about the nature of knowledge and scientific inquiry itself. How can we study or validate the existence of other universes if they lie beyond our observable horizon? This dilemma invites discussions about the limits of scientific methodology and the nature of empirical evidence. It pushes us to examine the boundaries of what can be known and challenges the notion of a single, unifying scientific theory that addresses all aspects of existence. Lastly, there's the ethical dimension of these theories. If every conceivable version of reality exists, does that imply moral relativism? The existence of divergent universes where decisions vary could suggest that ethical landscapes are subjective and fluid. This invites us to contemplate our moral responsibilities and the implications of our choices within the vast tapestry of possible realities. Together, these questions illustrate how multiverse theories not only stretch the boundaries of science, but also delve deeply into philosophy, revealing the interconnectedness of understanding existence from multiple perspectives. The concept of time travel has fascinated scientists, philosophers, and science fiction enthusiasts alike, prompting explorations into the nature of time itself. Several theoretical frameworks in physics provide a foundation for the possibility of time travel, expanding our understanding of the universe. One of the most prominent theories comes from Albert Einstein's theory of relativity, which revolutionized how we perceive time and space. According to this theory, time is not a constant, independent dimension, but is woven together with the three spatial dimensions into a four-dimensional fabric called spacetime. This means that time can be affected by gravity and speed, leading to the interesting notion that moving near the speed of light could slow down time relative to an outside observer. Another fascinating concept arises from the idea of wormholes, speculative tunnels in space-time that could connect distant points in both space and time. Wormholes are derived from the equations of general relativity and propose shortcuts through the cosmos. If these theoretical passages exist and could be stabilized, they might permit travel through time as well as distance. However, creating and maintaining a traversable wormhole would require extraordinary conditions. including exotic matter with negative energy density, which has yet to be discovered or understood. Quantum mechanics also enters the conversation with its principles that challenge our classic understanding of time. The many worlds interpretation suggests that each decision or event could potentially create branches in time, leading to parallel universes. This would imply that time travel might not affect the past in a linear way as we traditionally conceive, but rather could lead to alternate timelines or realities. Such theories introduce a level of complexity and wonder about the nature of existence and historical events. Finally, the concept of cosmic strings, hypothetical one-dimensional defects in spacetime, adds another layer to the discussion of time travel. These immense strands, if they exist, could warp spacetime around them. Theoretically, moving around such a cosmic string at high speeds could provoke time loops, allowing an individual to revisit a previous moment. Although these ideas remain theoretical and far from practical implementation, they challenge our understanding of the universe and invite us to ponder the uncharted territories of time. Wormholes are one of the most fascinating concepts in theoretical physics, often appearing in discussions about time travel. Picture a wormhole as a tunnel that connects two separate points in spacetime. This idea stems from the general theory of relativity, which predicts the fabric of spacetime can be curved and distorted. While they remain purely theoretical to this day, wormholes represent a potential shortcut across the cosmos or even a bridge to different times. Current hypotheses suggest that if these wormholes could exist, they might allow for time travel under specific circumstances. In theory, if one end of a wormhole were to be accelerated to near the speed of light and then brought back, time could run differently at that end compared to the other. This creates an enthralling possibility. Stepping into one side of the wormhole could lead you to a different moment in time at the exit. However, significant challenges remain, not the least of which is the stability of these structures. They could collapse before anything could traverse them, making them a tantalizing yet elusive concept. Moreover, the topic opens a Pandora's box of paradoxes and questions about causality. If time travel were possible through wormholes, it raises intriguing scenarios. For instance, could someone travel back in time and alter events? This brings about what is known as the grandfather paradox. If one were to prevent their grandparents from meeting, would they still exist to make that trip back in the first place? These paradoxes remain purely theoretical and ignite debates among physicists and philosophers alike. Ultimately, while wormholes provide an exciting framework for understanding time travel, we are far from proving their existence or functionality. The exploration of this concept enhances our understanding of the universe and the complexities inherent within it, challenging us to rethink the very nature of time and the boundaries of science. As research in theoretical physics continues, the allure of time travel through wormholes remains a captivating dream, anchored in the mysterious depths of our cosmos. The grandfather paradox is perhaps the most famous time travel paradox, illustrating a fascinating problem in the realm of speculative physics. Imagine someone travels back in time and inadvertently prevents their grandfather from meeting their grandmother. If this were to happen, the time traveler would never have been born. This creates a contradiction. If the time traveler was never born, how could they have traveled back in time to change history in the first place? This paradox raises profound questions about the nature of time, causality, and our understanding of reality. Beyond the grandfather paradox, there are several other time travel paradoxes that have piqued the interest of both scientists and philosophers. One notable example is the predestination paradox. In this scenario, a time traveler goes back to ensure that a historical event occurs as it did. However, by doing so, they inadvertently become the cause of that event, leading to a loop in which the future and past are intertwined. This loop challenges our intuitive notion of cause and effect. Another thought-provoking idea is the many worlds interpretation. This theory suggests that every time a decision is made or an event occurs, the universe splits into multiple realities. In this framework, if a time traveler were to manipulate the past, they would not create contradiction, but rather branch off into an alternate timeline. Each timeline remains valid, helping to resolve the paradox to some extent. These alternate realities expand the discussion about free will, fate, and the consequences of our actions across time. While we currently lack the technology for time travel, these paradoxes encourage rich discussions about the fundamental nature of time itself. They challenge our perceptions and ignite the imaginations of scientists and dreamers alike, prompting us to consider what lies beyond the fabric of our universe. In exploring these theories, we delve deeper into the mysteries of existence and our place within the cosmos. Time travel has long captured the human imagination, spurring discussions about its feasibility among scientists and philosophers alike. At the core of the theory lies the concept of causality, the principle that every cause has a corresponding effect and that events unfold in a linear sequence. If time travel were to exist in our universe, it could lead to paradoxes that disrupt this fundamental principle, such as the famous grandfather paradox, where a time traveler could potentially prevent their own existence. To explore the possibilities of time travel without breaching causality, scientists often turn to theoretical frameworks like Einstein's theory of relativity. This groundbreaking understanding of space and time posits that time is not a fixed entity, but is intertwined with the fabric of the universe itself. Under certain conditions, such as near a black hole or through hypothetical constructs like wormholes, it might be possible to move between different points in time. These scenarios suggest that time could be traversed without creating contradictions in cause and effect. Some researchers propose models using closed time-like curves, paths through space-time that circle back on themselves. These curves could allow for the potential return to the same point in time while avoiding direct consequences that could disrupt earlier events. In this view, time travel does not necessarily mean altering past events, but rather experiencing them from a different perspective without fundamentally changing the timeline. Moreover, the many worlds interpretation of quantum mechanics offers another intriguing resolution to the dilemma of causality and time travel. This interpretation suggests that every action spawns new branches of reality. Thus, if time travel were ever realized, a traveler might create an alternate timeline rather than affecting their original timeline. This fascinating idea allows for the existence of time travel while respecting the causal structure of our universe, hinting at the profound complexity underlying time itself. Quantum mechanics, the branch of physics that explores the behavior of tiny particles at the atomic and subatomic levels, adds a fascinating dimension to the question of time travel. Unlike the classical mechanics that govern larger objects and predictable paths, quantum mechanics introduces a realm of probabilities and uncertainties. This very nature opens the door to some intriguing possibilities for time travel, although it also raises complex questions. At the heart of quantum mechanics is the concept of superposition, where particles can exist in multiple states at once until they are observed. This principle invites speculation about alternate timelines and parallel universes. If multiple realities can coexist, could it be possible to traverse between these different states of existence? Some theorists suggest that time travel might not be about moving through time in the classical sense, but rather switching between different versions of reality that exist simultaneously. Another critical aspect is entanglement, where particles become linked and the state of one instantly influences the other, regardless of distance. This phenomenon challenges traditional notions of locality and suggests that information might not be confined by the constraints of time and space as we understand them. If time travel were to become feasible, it could potentially involve manipulating such quantum entanglements to navigate through time. However, the implications of quantum mechanics also come with their own paradoxes and challenges. For instance, while speculative theories like wormholes appear to be theoretically possible, creating and maintaining stable openings for travel through time would require conditions and materials that are currently beyond our reach. Thus, while quantum mechanics enriches the dialogue about time travel and keeps the curiosity alive, our current understanding still leaves us far from practical possibilities for actual time travel. Imagine the universe as a vast fabric, woven together by the threads of space and time. Within this cosmic tapestry, scientists postulate the existence of unusual structures known as cosmic strings. These hypothetical constructs arise from a variety of theories in physics, particularly those relating to the early moments of our universe. Essentially, cosmic strings are one-dimensional defects in the fabric of space-time itself, thought to form during phase transitions in the early universe's cooling process. The intriguing aspect of cosmic strings lies in their immense gravitational influence. The gravity they exert can warp the surrounding space-time, creating paths or shortcuts that could, in theory, be used for time travel. If two cosmic strings were positioned nearby each other, their effects could potentially create a scenario where space-time is bent in such a manner that traveling along these deformed regions might allow one to move back and forth through time. Essentially, the intense gravitational pull of these strings could enable a traveler to loop back to an earlier point in time. Furthermore, some scientists propose that if a spacecraft could maneuver around cosmic strings fast enough, it might harness this warping of space-time to achieve time travel. This echoes the principles of Einstein's theory of relativity, which shows that, under certain conditions, time is not a constant but can be stretched and compressed depending on the speed and gravitational field one experiences. Each of these theories challenges our conventional understanding of time and invites us to ponder the fascinating possibilities that may exist beyond our three-dimensional perceptions. However, despite the tantalizing theories surrounding cosmic strings and their time-traveling potentials, it is crucial to remember that they remain speculative. Cosmic strings have not yet been detected, nor is there empirical evidence to support the practical ways they might facilitate time travel. This tantalizing blend of theoretical physics and the unknown continues to spark curiosity and debate in the scientific community, illustrating our ongoing quest to understand the very fabric of the universe. The ultimate fate of the universe is a tantalizing question at the forefront of cosmological research. Scientists have proposed several scenarios, each based on the universe's expansion rate, the density of its matter, and the mysterious influence of dark energy. Currently, one of the most widely discussed outcomes is known as the Big Freeze. In this scenario, the universe continues to expand indefinitely, leading to the gradual cooling of stars and galaxies. Over billions of years, stars will burn out, leaving behind cold remnants, and eventually, matter will drift apart until the cosmos becomes a dim, dark expanse filled with lonely particles. An alternative theory is the Big Crunch. In this scenario, the gravitational forces within the universe might become strong enough to halt the expansion and reverse it, causing all matter to collapse back into an infinitely dense point. This would be a profound return to a state similar to the Big Bang. However, current observations suggest that dark energy, which drives the accelerated expansion of the universe, may render this scenario increasingly unlikely. Another possibility is the Big Rip. This scenario hinges on the idea that dark energy could become increasingly powerful, tearing apart galaxies, stars, and eventually even atoms as the universe reaches a critical point. In this dramatic end, all structures would be unmade in a catastrophic expansion that leaves nothing intact. While this concept sounds extreme, it reflects ongoing research into the behavior of dark energy and its implications for the future of the cosmos. Finally, we cannot ignore the notion of oscillating or cyclic universes, where the universe undergoes a series of expansions and contractions. In this viewpoint, after experiencing a big crunch, it could potentially lead to another Big Bang, creating an endless circle of cosmic rebirth. Each of these scenarios opens a window into profound questions about the laws of physics and the nature of existence itself, encouraging us to explore the universe's mysteries even further. The concept of heat death offers a fascinating and somewhat eerie perspective on the universe's eventual fate. This theory posits that the universe will reach a state of maximum entropy, a condition where all energy is evenly distributed and there are no temperature differences. In simpler terms, every part of the universe would be at the same temperature, rendering any form of work or energy transfer impossible. Think of it as the universe running out of usable energy, akin to a battery that has fully drained. As the universe expands over billions of years, galaxies will move further apart, stars will burn out, and existing stars will exhaust their nuclear fuel. The process will be incredibly gradual, but ultimately, stellar formation will cease, and the cosmos will be populated mostly by white dwarfs, neutron stars, and black holes. Over immense timescales, these remnants of stars will fade, leaving behind a cold, dark universe filled only with radiation and elementary particles. In this darkened landscape, the heat death signifies a silent cosmos. With energy uniformly spread out, there would be no areas of higher energy to drive processes or reactions. Life, as we know it, would be impossible in such a stagnant environment. The universe would have transitioned from a vibrant tapestry of cosmic activity to a tranquil yet lifeless expanse, devoid of any structured formations or processes. The heat death theory compels us to consider our existence in a universe governed by profound laws of thermodynamics. It serves as a stark reminder of the transient nature of stars and galaxies, as well as the ultimate fate awaiting everything we see around us. The universe, once a cradle of galaxies and stars, will slowly succumb to uniformity, reminding us of the delicate interplay of energy, time, and the inevitable march toward entropy. The Big Crunch hypothesis presents a dramatic vision for the ultimate fate of our universe. At its core, this theory suggests that the expansion of the universe, which has been occurring since the Big Bang, could one day reverse. Imagine a universe that has been moving outward for billions of years, where galaxies drift apart, only to find itself pulled back into a singular point due to gravitational forces. This hypothesis theorizes that all matter and energy in the universe could eventually converge back to an infinitely dense state. In the early days following the Big Bang, the universe began as an incredibly hot and dense point. Over time, space itself expanded, allowing galaxies to form and stars to ignite. However, the Big Crunch posits that this expanding epoch could slow and stop, eventually reversing the trend. If the gravitational attraction of all the universe's matter is strong enough, it would overcome the current trajectory of expansion, leading to a gradual deceleration and ultimately a retraction of space itself. As the universe begins to contract, galaxies would shift closer together and cosmic structures would collapse. The temperature would rise dramatically as everything converges, potentially reigniting processes similar to those of the initial Big Bang. This would lead to a state of extreme density where the entire cosmos could return to its original hot and dense state, possibly marking the end of time as we know it. The implications of the Big Crunch are profound, prompting critical reflections on the nature of time, space, and cosmic existence. While current observations suggest that the universe's expansion is more likely to continue indefinitely, potentially leading to scenarios like the Big Freeze, this hypothesis serves as an important counterpoint in our understanding of cosmic evolution. By contemplating the possibilities of contraction, we not only engage with fundamental questions about our universe's destiny, but also the very essence of reality itself. Imagine a universe governed by a mysterious force known as dark energy, which is believed to be driving the accelerated expansion of space. In this potential Big Rip scenario, dark energy could get stronger over time, leading to dramatic consequences for the cosmos. As the universe continues to expand, galaxies would eventually find themselves racing away from one another at increasingly faster speeds. This relentless separation could set the stage for a catastrophic fate. In the early stages, galaxies may drift apart, with the space between them stretching like a rubber band. Over millions, perhaps billions of years, this stretching would become more pronounced, impacting clusters of galaxies. Eventually, even galaxies themselves could be torn apart as the gravitational forces holding them together begin to weaken under the strain of this unrelenting expansion. As we progress toward the ultimate moments of the Big Rip, the gravitational forces within stars and planets would not be immune to dark energy's growing influence. The bonds that hold atoms together might also unravel, culminating in a chaotic dissolution of matter itself. This means that not only would galaxies be ripped apart, but the very fabric of atoms and subatomic particles could be torn asunder. In the final stages of this scenario, the universe would be a tumultuous place. Stars, planets, and every form of matter would disintegrate into a vast, empty ocean of energy. The Big Rip poses profound questions about the fate of our universe, challenging scientists to understand not only the nature of dark energy, but how it shapes the very structure of everything we know. As we gaze into the vastness of space, recent observations have begun to illuminate the fate of our universe with startling clarity. Astronomers have long debated various outcomes, but the most compelling insights arise from studying the universe's expansion. Using advanced telescopes and surveys, scientists have discovered that the universe is not only expanding, but that this expansion is accelerating. This remarkable revelation stems from the properties of dark energy, a mysterious force thought to make up about 70% of the universe's total energy budget. Dark energy challenges our understanding of gravity and the nature of the cosmos. As galaxies drift apart, propelled by this enigmatic force, it raises profound questions about how the universe will ultimately evolve. Current models suggest that if dark energy continues its dominance, the universe may be headed toward what is known as the Big Freeze. This scenario envisions a future where the expansion continues indefinitely, leading to increasingly cold and isolated remnants of stars and galaxies. Over trillions of years, stars will burn out, leaving behind a dark, empty cosmos. Alternatively, some theories speculate about different cosmic fates that could unfold, such as the Big Crunch or the Big Rip. The Big Crunch would occur if gravity eventually overcomes dark energy, causing the universe to slow, halt, and then reverse its expansion, collapsing back into a singularity. The Big Rip, on the other hand, posits that the intensity of dark energy might increase over time, tearing apart galaxies, stars, and eventually atoms themselves, resulting in a dramatic end to the fabric of reality as we know it. These insights are not merely theoretical musings. Observations of distant supernovae and measurements of cosmic microwave background radiation provide a tangible backdrop to our understanding. As scientists delve deeper into the cosmos, questioning not just what we see, but how we see it, the fate of the universe remains one of science's greatest puzzles. Each new discovery offers tantalizing clues about the ultimate destiny of everything beyond our planet, a journey into the unknown that beckons all who ponder the vast questions of existence. Cosmologists delve into the concept of entropy to predict the distant future of the universe. Entropy, at its core, measures the degree of disorder or randomness in a system. In the world of thermodynamics, systems naturally progress toward a state of greater entropy over time. This principle, known as the second law of thermodynamics, implies that the universe is constantly moving toward higher levels of disorder. As cosmologists study the universe's evolution, they recognize that this trend of increasing entropy shapes its ultimate fate. In considering the far future, researchers anticipate a scenario named the heat death of the universe. As stars eventually burn out and galaxies drift apart, the cosmos will reach a state where energy is uniformly distributed. There will be no significant gradients of temperature or energy to exploit. This means that all processes, including those that sustain life, may cease. Thus, the universe's journey toward maximizing entropy leads to a lifeless, cold state in which matter becomes inert. By analyzing the current state of the cosmos, including the distribution of galaxies and cosmic microwave background radiation, scientists can make educated estimates about entropy levels. They employ mathematical models to simulate future conditions, reflecting on how energy transitions from one state to another. These models help cosmologists project how long it will take for stars to extinguish, how black holes will evaporate, and ultimately, when the universe will settle into this state of equilibrium. The insights gained from studying entropy thus provide a profound understanding of the cosmic timeline. They suggest an inevitable shift toward ultimate stillness and uniformity, highlighting the delicate balance that governs the universe. Through this lens, the enigmatic evolution of our cosmos, from its fiery beginnings to its serene, entropy-driven conclusion, captivates both the imagination and intellect of those who ponder the mysteries of existence. Dark energy is one of the most enigmatic components of our universe, accounting for approximately 70% of its total energy density. Its discovery has reshaped our understanding of cosmology, particularly concerning the fate of the universe. Unlike matter, which pulls objects together through gravitational attraction, dark energy exerts a repulsive force, driving galaxies apart at an accelerating rate. This puzzling phenomenon suggests that the universe is not only expanding, but doing so at an ever-increasing speed. As astronomers monitor distant supernovae and the cosmic microwave background radiation, they have uncovered compelling evidence for this acceleration. The implications are profound. If dark energy continues to dominate the dynamics of the universe, it may lead to various scenarios for its ultimate fate. One potential outcome is known as the Big Freeze, where galaxies drift further and further away from each other, resulting in a cold, dark universe where stars eventually burn out and become extinct. Another possibility is the Big Rip, a more dramatic endgame where dark energy becomes increasingly potent, tearing apart galaxies, stars, and even atomic structures. In this scenario, the universe would experience a final cataclysmic dissolution as everything is pulled apart. Though both fates seem distant, perhaps tens of billions of years away, each provides a tantalizing glimpse into the long-term future of our cosmos. Thus, dark energy is not just a mysterious force, it is a vital ingredient in predicting the universe's destiny. Challenging our understanding of physics, it invites further exploration into the rules governing the cosmos, urging scientists to unravel its secrets and understand how it influences the grand narrative of existence.